universe is full of mysteries that have puzzled humanity for ages. What are the true natures of black holes, and what happens beyond their event horizons? Could there be multiple universes, each with its own unique laws of physics? Join us on a journey through the unknown, as we seek answers to the universe's biggest mysteries. Neutron stars are the remnants of massive stars that have ended their life cycle in a spectacular supernova explosion. These enigmatic objects are incredibly dense, so much so that a sugar cube-sized amount of neutron star material would weigh about 1 billion tons on Earth. Essentially, neutron stars are cosmic densification at its extreme, packing the mass of our Sun into a sphere with a radius of roughly 10 kilometers. The core of a neutron star is believed to contain matter in a state that's not found anywhere else in the universe, a bizarre substance where protons and electrons have fused together to form neutrons under the intense pressure. Their magnetic fields are also astoundingly strong, billions of times stronger than the Earth's, leading to phenomena that we don't yet fully understand. If all this wasn't strange enough, neutron stars can also spin at phenomenal rates, some rotating as fast as 700 times per second. These rapidly spinning neutron stars are known as pulsars and emit beams of radiation that sweep across the sky like cosmic lighthouses. To an external observer, these beams appear to pulse with great regularity, hence the name. This peculiar combination of density, magnetic fields, and rotational velocity makes neutron stars some of the most fascinating and perplexing objects in the cosmos. Black holes form from the gravitational collapse of massive stars at the end of their life cycles. When such a star exhausts its nuclear fuel, it can no longer support itself against gravitational forces. If the remnant core is above a certain mass, not even neutron degeneracy pressure can halt the collapse, resulting in a black hole. This creates a region in space where gravity is so strong that not even light can escape, a boundary known as the event horizon. The point at the center, where all the mass is thought to be condensed into an infinitely small space, is called a singularity. Here, the laws of physics as we know them break down, making the singularity one of the most profound mysteries in cosmology. Black holes also challenge our understanding of time and space. They warp the fabric of space-time to such an extent that time behaves differently near them. This has led to fascinating, albeit theoretical, ideas like time dilation, where time can slow down for someone close to a black hole compared to someone farther away. Additionally, black holes are thought to harbor essential clues to the nature of quantum physics and general relativity, two pillars of modern physics that currently don't fully reconcile with one another. The event horizon itself raises questions about information paradoxes, as it's debated whether information that falls into a black hole is lost forever or somehow preserved. Adding to the intrigue, some theories propose that black holes could be gateways to other dimensions, or even entirely different universes, making them not just pillars of immense gravitational force, but also cosmic riddles awaiting solutions. A magnetar is a type of neutron star characterized by an extraordinarily powerful magnetic field, often more than 1,000 times stronger than that of typical neutron stars and over a quadrillion times stronger than Earth's magnetic field. These intense magnetic fields are the result of the star's rapid rotation and the presence of superfluid cores. As the massive progenitor star collapses into a neutron star, its magnetic field gets immensely amplified. This process, known as the dynamo mechanism, can crank up the magnetic field to such extreme levels. The powerful magnetic fields of magnetars can cause some truly extraordinary phenomena. For instance, they can occasionally undergo starquakes, similar to earthquakes but on a stellar scale, which release enormous amounts of energy and can produce giant flares observable across vast distances in space. The magnetic field is so strong that it influences the atomic structure of matter in its vicinity, creating conditions that can't be replicated in any earthbound laboratory. Magnetars' immense magnetic fields can also disrupt the electronic arrangements in atoms, making their spectra different from that of normal matter. This makes magnetars not just fascinating but also pivotal in helping us understand the behavior of matter under extreme magnetic conditions, offering a glimpse into realms that lie far beyond our everyday experiences. White dwarfs are the remnants of stars that were once similar to our Sun but have exhausted their nuclear fuel. Unlike massive stars that end their lives in supernova explosions, stars with relatively low to medium mass shed their outer layers, leaving behind a dense, compact core. This core becomes a white dwarf, typically around the size of Earth, but with a mass around half that of the Sun. Despite their small size, white dwarfs have a density that's extraordinarily high. A single teaspoon of white dwarf material would weigh several tons. One of the unique aspects of white dwarfs is that they do not generate energy through nuclear fusion, which sets them apart from main sequence stars and other stellar types. Instead, they shine due to residual thermal energy, slowly cooling and fading over billions of years. This cooling process allows astronomers to estimate the ages of white dwarf populations, contributing to our understanding of stellar evolution and the age of our galaxy. White dwarfs also provide a natural laboratory for studying quantum mechanics on a macroscopic scale, particularly the principles of electron degeneracy pressure, which supports them against gravitational collapse. This degeneracy pressure arises from the Pauli exclusion principle, which states that two electrons cannot occupy the same quantum state, creating a force that counterbalances the star's gravitational pull. The study of white dwarfs also offers insights into future cosmic events. For example, it's believed that our own Sun will eventually become a white dwarf, providing a glimpse into the distant fate of our solar system. Additionally, in binary systems where a white dwarf accretes matter from a companion star, it can lead to various phenomena, including novae or even supernovae under certain conditions, enriching the interstellar medium with heavier elements. This interplay of physics and stellar evolution makes white dwarfs unique and indispensable for our understanding of the cosmos. Rogue planets, also known as interstellar planets or nomad planets, are planetary mass objects that drift through space without being gravitationally bound to any star. These dark wanderers are intriguing because they defy the typical life cycle of planets, which usually form in the accretion disks of young stars and remain in orbit around their parent stars. There are several theories about how rogue planets come to roam the cosmos independently. One possibility is that they are ejected from their original star systems due to gravitational interactions, either with other planets or passing stars. Such chaotic orbits can sometimes result in a planet being flung out of its star's gravitational influence altogether. Additionally, rogue planets might form in isolation, far away from a star. In the cold, dense regions of molecular clouds, it's possible for gas and dust to collapse directly into a planet-sized object without ever forming a star. These free-floating formations would bypass the traditional stellar system entirely, emerging as fully fledged planets with no sun to call their own. Their existence raises fascinating questions about planetary formation theories and the overall architecture of our galaxy. The detection of these elusive bodies has been challenging due to their lack of a stellar host to illuminate them. However, advances in observational techniques, such as gravitational microlensing, have allowed astronomers to identify rogue planets by the way their gravity warps the light of background stars. The absence of a nearby star also means that these planets are extremely cold, with surfaces that could be composed of exotic forms of ice and rock. If they have substantial internal heat, courtesy of radioactive decay or residual formation heat, some rogue planets could theoretically harbor subsurface oceans. This tantalizing possibility suggests that life, if it exists, could be found in some of the most unexpected corners of the universe. The Oort cloud is a hypothetical, vast spherical shell of icy objects that exists at the outermost edge of our solar system, believed to be located roughly between 2,000 and 100,000 astronomical units from the Sun. Named after the Dutch astronomer Jan Oort, who first proposed its existence, the Oort cloud is thought to be the origin of long-period comets that take thousands of years to complete a single orbit around the Sun. Unlike the relatively flat Kuiper belt, which lies beyond Neptune's orbit, the Oort cloud forms a distant, nearly spherical swath that envelops the entire solar system. The secrets held within the Oort cloud could provide critical information about the early solar system. It's believed that these icy bodies are remnants from the solar system's formation over 4.5 billion years ago, essentially frozen time capsules preserving the primordial material from which the Sun, planets, and other celestial objects formed. By studying the composition of comets that journey toward the Sun from the Oort cloud, scientists hope to unlock clues into the conditions and processes that prevailed in the early solar nebula. These comets often contain complex organic molecules, hinting at the raw ingredients for life that were present in the nascent solar system. Moreover, investigating the Oort cloud can enhance our understanding of gravitational influences in the stellar nursery where our Sun formed. The cloud's formation likely involved intricate gravitational encounters with passing stars and the tidal forces from the Milky Way's galactic core. As a result, analyzing the Oort cloud's distribution and dynamics could provide valuable data on the solar system's interactions with its galactic environment. Though no spacecraft has yet ventured into this distant domain, future missions might enable direct sampling and exploration, offering profound insights into the origins and evolution of our celestial neighborhood. Pulsars are a specific type of neutron star that emits beams of electromagnetic radiation from their magnetic poles. These beams are incredibly consistent, leading to the pulsar's characteristic regular pulsing appearance as viewed from Earth. The precision of these pulses can be likened to the regular ticking of a cosmic clock. Pulsars are formed from the remnants of massive stars that undergo supernova explosions. When the core of such a star collapses, it results in a neutron star with an incredibly high rotational speed and a powerful magnetic field. The fundamental mechanism behind the regular pulses of radiation lies in the misalignment between the neutron star's rotation axis and its magnetic axis. As the neutron star spins, its intense magnetic field accelerates charged particles to near-light speeds along magnetic field lines, focusing them into tight beams of radiation emanating from the magnetic poles. If these magnetic poles are not aligned with the rotational axis, the beams sweep across space like the beams of a lighthouse. When these beams sweep past Earth, they create the detectable pulses of radiation. Pulsars also play a significant role in various areas of astrophysics and general relativity. The timing precision of pulsar signals allows astronomers to test the limits of gravitational theories and conduct experiments that would be impossible under Earth-bound conditions. For instance, measurements of binary pulsar systems, where two neutron stars orbit each other, have provided some of the most precise confirmations of Einstein's theory of general relativity. Additionally, the discovery of extremely fast-spinning millisecond pulsars has shed light on the interplay between accreting material from companion stars and the resultant spin-up effect on older neutron stars. This makes pulsars not only fascinating objects in their own right, but also invaluable tools for probing the fundamental laws of physics. A quasar, or quasi-stellar object, is an incredibly luminous and active galactic nucleus powered by a supermassive black hole at its center. These cosmic beacons can emit more light than an entire galaxy, but their dazzling luminosity originates from a relatively compact region. As matter spirals into the supermassive black hole, it forms an accretion disk where gravitational energy is converted into immense heat and light. The intense radiation, often spanning across the entire electromagnetic spectrum, from radio waves to gamma rays, results from this energetic infall of gas and dust. Quasars are visible across vast cosmic distances, serving as profound indicators of activity in the early universe. Quasars hold a treasure trove of information about the early universe. They are often found at great distances from Earth, meaning we observe them as they were billions of years ago, soon after the Big Bang. By studying quasars, astronomers can glean insights into the conditions that prevailed during the formative epochs of the universe. Their high redshifts, a measure of how their light is stretched to longer wavelengths by the expansion of the universe, give vital clues about the rate of cosmic expansion and the distribution of matter across large scales. Moreover, quasars illuminate the intergalactic medium, the diffuse gas that exists between galaxies, enabling scientists to map the distribution of elements and the large-scale structure of the cosmos. The absorption lines in quasar spectra reveal the chemical composition, temperature, and density of intervening gas clouds, offering indirect evidence about the processes happening in the early universe. Quasars also help us understand the growth and evolution of supermassive black holes and their host galaxies. By exploring the connection between quasars and galaxy formation, researchers can piece together the storyline of how the large-scale structure we see today came into being. Through these luminous objects, we gain a deeper appreciation of the dynamic, ever-evolving universe that surrounds us. Cosmic rays are high-energy particles that originate from various sources in the universe, including the Sun, distant stars, supernova, and even more exotic events like gamma-ray bursts and active galactic nuclei. These particles, primarily protons and atomic nuclei, travel at nearly the speed of light and can have energies far exceeding those produced by human-made accelerators. One major origin of cosmic rays is supernova remnants, where shock waves from exploding stars accelerate particles to immense speeds through processes like Fermi acceleration. The effects of cosmic rays on the universe are manifold and significant. When cosmic rays enter the Earth's atmosphere, they collide with atmospheric molecules, creating a cascade of secondary particles known as air showers. This interaction contributes to the ionization of the atmosphere, which can influence weather patterns and cloud formation. Cosmic rays also produce isotopes like carbon-14, which are invaluable for radiocarbon dating techniques used to determine the age of archaeological and geological samples. Moreover, cosmic rays play a crucial role in astrophysics and cosmology. Their interactions with interstellar and intergalactic matter provide insights into the composition and dynamics of cosmic environments. Studying cosmic rays helps scientists understand extreme astrophysical processes and the conditions in distant parts of the cosmos. Additionally, cosmic rays contribute to the background radiation that permeates space, known as cosmic background radiation, which serves as a tool to probe fundamental physics. On a broader scale, cosmic rays can also affect biological and technological systems. High-energy particles pose a threat to astronauts in space and can compromise the integrity of onboard electronics and satellites. Understanding cosmic rays and developing shielding mechanisms is essential for the future of deep space exploration. Cosmic rays are not just high-energy particles zooming through space. They are vital messengers carrying secrets about the universe's most energetic phenomena and its evolutionary history. Dark matter plays a pivotal role in the universe, acting as the invisible scaffolding that holds galaxies and cosmic structures together. Unlike ordinary matter, dark matter does not emit, absorb, or reflect light, making it undetectable through conventional telescopes. Its presence is inferred from its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. For instance, the rotational speeds of galaxies can't be explained merely by the gravitational pull of the observable stars and gas. These speeds indicate that a substantial amount of unseen mass is present, providing the necessary gravitational force to hold these galaxies together. Detecting dark matter is one of the biggest challenges in astrophysics and cosmology. There are several methods researchers use to infer its presence and properties. One approach is gravitational lensing, where light from distant objects is bent around massive, unseen objects, including dark matter, creating distorted and magnified images of those objects. This method allows astronomers to map the distribution of dark matter in galaxy clusters. Another approach is studying cosmic microwave background (CMB) radiation, the residual thermal radiation from the Big Bang. Tiny fluctuations in the CMB provide clues about the universe's composition and the influence of dark matter during its early stages. On the terrestrial front, scientists employ highly sensitive detectors deep underground or in isolated environments to search for potential dark matter particles, such as weakly interacting massive particles, WIMPs or axions. These detectors aim to identify rare interactions between dark matter particles and ordinary matter. Additionally, particle accelerators like the Large Hadron Collider, LHC, attempt to produce dark matter particles by recreating high-energy conditions similar to those just after the Big Bang. Despite our inability to observe dark matter directly, its gravitational influence is indispensable for explaining the formation and evolution of cosmic structures. Understanding dark matter could revolutionize our grasp of fundamental physics, potentially revealing new particles and forces that govern the universe. Through these meticulous and diverse detection efforts, scientists hope to unlock one of the most profound mysteries in modern astrophysics. The multiverse theory posits that our universe is just one of potentially countless others, each with its own distinct set of physical laws, constants, and conditions. This concept challenges the traditional notion of a singular, all-encompassing cosmos. The multiverse idea emerges from various areas of theoretical physics and cosmology, including string theory, quantum mechanics, and cosmic inflation models. For instance, in the aftermath of the Big Bang, rapid inflation could have given rise to multiple bubble universes, each constituting a separate realm with unique properties. One of the profound implications of the multiverse theory is its impact on the Theanthropic Principle, which tries to explain why the physical constants of our universe appear finely tuned to allow the existence of life. If there are countless universes each with different properties, it's plausible that we find ourselves in one of the few where conditions are just right for life to develop. This shifts the perspective from seeing our universe's characteristics as extraordinarily special to them being one of many possible outcomes. The multiverse theory also has significant philosophical and scientific implications. It challenges our understanding of reality, suggesting that what we perceive as the universe may be a tiny fragment of a vastly larger and more complex cosmic structure. If true, this could mean that every possible history or outcome is realized in some part of the multiverse, creating a virtually infinite tapestry of realities. However, one of the biggest challenges with the multiverse theory is its testability. Since other universes would exist outside our observable horizon, directly detecting them with current technology or methodologies is a colossal hurdle. This raises questions about the scientific validity of the theory, as it currently resides more in the realm of philosophical speculation than empirical science. Nonetheless, the multiverse remains a captivating possibility, pushing the boundaries of our imagination and understanding and prompting us to rethink the very fabric of existence. Parallel universes, often referred to as alternate or parallel realities within the broader multiverse theory, are hypothetical realms where the fundamental properties of physics, timelines, and events can differ from those in our own universe. While the idea of parallel universes is still speculative, several intriguing hypotheses propose how they might differ from our reality. For example, in some versions, these universes might have physical constants or laws of nature that vary significantly, leading to entirely different types of matter, forces, and even life forms, if life could exist under those conditions at all. In others, these universes could resemble our own, but differ in key historical events, such as which galaxies formed or major outcomes in the evolution of life. The concept of parallel universes also introduces the tantalizing possibility of intersections or interactions with our own universe. Some theoretical frameworks, such as the many worlds interpretation of quantum mechanics, suggest that every possible outcome of a quantum event actually occurs in a separate branching universe. Although these branches typically remain isolated, conceptual overlaps like quantum entanglement or wormholes have been suggested as potential mechanisms for interaction. Another intriguing idea is the concept of brane cosmology from string theory, where our universe is a three-dimensional brane floating in a higher dimensional space, occasionally interacting with other branes. The implications of intersecting parallel universes are as profound as they are challenging to prove. If such intersections were possible, they could potentially result in observable anomalies, such as sudden and inexplicable changes in the physical laws or unexpected cosmic phenomena. Overall, the concept of parallel universes invites us to contemplate profound questions about the nature of reality, causality, and existence itself. While currently residing on the fringes of scientific investigation, advancements in quantum physics, cosmology, and related fields may one day provide the tools to explore these fascinating possibilities more concretely. Until then, parallel universes remain a thought-provoking hypothesis, pushing the boundaries of our comprehension and imagination. The concept of a bubble universe is a fascinating aspect of the multiverse theory, particularly within the framework of cosmic inflation. According to this idea, our universe is just one of potentially countless bubbles that have formed in a vast, inflating cosmic landscape. This concept emerges from the inflationary theory, which proposes that a rapid and exponential expansion of space occurred fractions of a second after the Big Bang. During this inflationary period, different regions of space could have inflated at different rates, leading to the formation of isolated bubble universes, each with its own distinct physical properties and constants. In relation to the Big Bang, the bubble universe model extends the concept of a singular universe-creating event to a broader context. Instead of one explosive event giving birth to a single universe, the Big Bang could be seen as the local manifestation of inflation within our particular bubble. In this scenario, the larger inflating space, the multiverse, is constantly spawning new bubble universes through similar processes of rapid expansion. Each bubble universe could experience its own Big Bang, leading to a localized environment with its own unique set of rules and characteristics. The implications of the bubble universe concept are profound and far-reaching. It suggests that what we perceive as our entire universe is just one small part of a much larger, possibly infinite cosmological structure. Each bubble could contain its own galaxies, stars, and perhaps life forms, fundamentally altering our understanding of existence and our place within it. Moreover, the interactions between bubble universes, if they occur, could yield observable phenomena such as gravitational waves, cosmic imprints, or exotic particles. However, the bubble universe theory presents significant challenges for empirical validation. The immense distances and potential barriers between bubbles make direct observation currently unfeasible. Nonetheless, advances in cosmological research, such as the study of the cosmic microwave background, CMB radiation and high-energy particle physics, might one day provide indirect evidence supporting this intriguing hypothesis. The bubble universe concept thus remains an exciting frontier in theoretical physics and cosmology, expanding the boundaries of our understanding of the universe and its origins. String theory is a theoretical framework that seeks to reconcile quantum mechanics and general relativity by positing that the fundamental constituents of the universe are not zero-dimensional point particles, but rather tiny one-dimensional strings. According to string theory, these strings vibrate at different frequencies, with each vibrational mode corresponding to a different particle, thereby unifying the diverse particles and forces within a single model. One of the most compelling aspects of string theory is its requirement for additional spatial dimensions beyond the familiar 3 dimensions of space and 1 dimension of time that we experience in everyday life. In its simplest forms, string theory suggests the existence of 10 or 11 dimensions, depending on the specific variant of the theory, such as Type 1, Type YA, Type UIB, heterotic SO, 32, heterotic EX-E8, or M theory, which posits 11 dimensions. These extra dimensions are thought to be compactified or curled up at scales so small that they are imperceptible to current experimental detection. The mathematical consistency of string theory relies on these additional dimensions. They provide the necessary degrees of freedom for the vibrations of the strings and allow for the unification of the fundamental forces, including gravity. Understanding these multiple dimensions can be quite abstract. Imagine a 2-dimensional surface like a sheet of paper. To a tiny ant crawling on that sheet, the paper appears 2-dimensional. But if you were able to fold or roll the paper into a tube, the ant might not perceive the 3rd dimension we've introduced. Similarly, the extra dimensions in string theory are thought to be compactified in such a way that they are hidden from our macroscopic view, but are crucial for the fundamental workings of the universe at the smallest scales. The implications of multiple dimensions are profound and manifold. For one, they could provide a solution to long-standing puzzles in physics, like the hierarchy problem, which deals with the vast difference in strength between gravity and the other fundamental forces. Additional dimensions might also offer new insights into the nature of black holes, the origins of the universe, and the very fabric of space-time. However, verifying the existence of these dimensions remains one of the most significant challenges. While indirect evidence might come from high-energy experiments, such as those conducted in particle accelerators like the Large Hadron Collider, or from cosmological observations, direct empirical confirmation is still elusive. Ultimately, string theory enriches our understanding of the universe by suggesting a more intricate, multi-dimensional tapestry of existence, challenging us to rethink the fundamental nature of reality in ways both profound and extraordinary. The shape of the universe is a profound concept that significantly impacts its expansion. Cosmologists typically consider 3 main possible shapes: flat, open, and closed. These shapes are derived from Einstein's theory of general relativity, and are intricately linked to the universe's overall geometry and density. In a flat universe, the geometry conforms to Euclidean principles, where parallel lines never converge or diverge. This suggests that the universe has just the right amount of density, often called the critical density. If the universe is flat, its expansion will continue forever, but at an ever-decreasing rate. Conversely, an open universe is shaped like a saddle with a negative curvature. Here, the density is lower than critical, which means the universe will keep expanding forever, but unlike the flat universe, it will do so at an accelerating rate. Lastly, a closed universe resembles the surface of a sphere, having a positive curvature with a density greater than the critical threshold. In this scenario, the expansion would eventually halt and reverse, leading to a big crunch, where the universe collapses back into a singularity. Understanding the universe's shape is pivotal because it influences the ultimate fate of everything within it, from galaxies to atoms. The holographic principle is a tantalizing and somewhat mind-bending idea emerging from the realms of quantum mechanics and string theory. It suggests that our entire three-dimensional universe might be describable by information encoded on a two-dimensional surface. Imagine a hologram on your credit card, where a two-dimensional image appears three-dimensional. Similarly, the holographic principle posits that all the information contained in our vast, spatially extensive universe could be represented on a distant, cosmological boundary. This principle has profound implications for our understanding of reality. It was initially formulated to resolve paradoxes involving black holes, particularly the issue of what happens to information that falls into a black hole. Traditional interpretations of physics suggested that this information would be lost forever, a notion conflicting with the laws of quantum mechanics. The holographic principle offers an elegant solution. The information is not lost, but rather stored on the black hole's event horizon, a two-dimensional boundary. If this principle holds true universally, it could mean that the fabric of our reality in 3 dimensions is deeply connected, or even synonymous, with this more fundamental two-dimensional description. This idea isn't just theoretical musing, it's backed by emerging research in theoretical physics, pushing the boundaries of how we conceptualize space, time, and reality itself. Wormholes, often referred to as Einstein-Rosen bridges, are theoretical passages through space-time that could act as shortcuts connecting distant regions of the universe, or perhaps even different universes. The concept stems from solutions to Einstein's field equations of general relativity, which depict gravitation as the curvature of space-time. In simplest terms, imagine space-time as a fabric. A wormhole is akin to folding this fabric, allowing 2 distant points to meet. If wormholes exist, they could revolutionize our understanding of travel and connectivity in the cosmos. Picture a wormhole as a tunnel with 2 ends, each situated in separate parts of space-time. Traversing a wormhole would mean entering at one mouth and exiting instantly at the other, bypassing the intervening space. This could theoretically permit faster-than-light travel and, intriguingly, time travel, depending on the nature of the wormhole's configuration and stability. However, creating or maintaining a traversable wormhole poses immense challenges. It would likely require exotic matter with negative energy density to prevent the tunnel from collapsing. Moreover, the idea of connecting to different universes enters the realm of the multiverse theory. If multiple universes exist, a wormhole could, in theory, link our universe to another, enabling transfers of matter, energy, or even information across entirely distinct cosmic domains. Although this remains speculative and well beyond our current technological and observational capabilities, the idea captivates both scientific and popular imaginations, challenging us to rethink the very boundaries of our universe. The existence of alternate realities or dimensions is one of the most captivating and contentious topics in modern science. While direct evidence remains elusive, several theoretical frameworks and indirect observations suggest their potential presence. One prominent piece of the puzzle comes from the field of quantum mechanics, specifically the famous many worlds interpretation. This interpretation posits that all possible outcomes of a quantum measurement actually occur, each in its own distinct universe. When a particle's state is measured, the universe allegedly splits, creating alternate realities for each possible outcome. Though we can't directly observe these parallel universes, the mathematics behind quantum mechanics aligns intriguingly well with this concept. Another line of evidence comes from string theory, suggesting a multidimensional universe. String theory posits that the fundamental constituents of reality are not zero-dimensional points, but one-dimensional strings vibrating at various frequencies. For the equations of string theory to be consistent, our universe must have additional spatial dimensions, 10 or 11, depending on the specific formulation. These extra dimensions are often thought to be compactified or curled up at microscopic scales, invisibly influencing the fabric of our four-dimensional space-time. Additionally, cosmological observations provide tantalizing hints. Phenomena like dark matter and dark energy, which constitute about 95% of the universe's total mass energy content and remain unexplained by current models, could be manifestations of interactions with higher dimensions or alternate realities. The cosmic microwave background radiation, the residual heat from the Big Bang, exhibits anomalies and patterns that some researchers suggest might be ripples from interactions with other dimensions or universes. So while we lack definitive proof of alternate realities or dimensions, multiple lines of theoretical and observational evidence keep the door open, continuously pushing the boundaries of our understanding and fueling the quest for deeper insights into the fabric of existence. Quantum mechanics, with its counterintuitive and often perplexing principles, lends robust theoretical support to the idea of multiple universes, primarily through the many worlds interpretation, MWI. According to traditional interpretations, a quantum system remains in a superposition of states until measured, at which point it seemingly chooses one state. The MWI challenges this by suggesting that all possible outcomes occur, but each in its own separate branching universe. Thus, every time a quantum event has several possible results, the universe splits into a corresponding number of parallel realities, each reflecting a different outcome. Imagine a simple quantum event, like the spin of an electron. According to MWI, if you measure the electron's spin, the universe bifurcates. In one branch, you'll find the electron with spin up, and in another, with spin down. This branching mechanism doesn't just apply to microscopic particles, but scales up to macroscopic events, meaning that every decision and action potentially spawns a new universe. Theoretically, this could lead to an almost unfathomable multitude of universes, each with its own unique history and future. Furthermore, the principles of quantum entanglement also bolster the concept of multiple universes. Entangled particles exhibit correlations that are inexplicable under classical physics, acting as though they are part of a single entity, even when separated by vast distances. In the MWI framework, these correlations can be understood as links across parallel universes, creating a kind of quantum tapestry woven from a myriad of realities. While this remains highly speculative, the mathematics underpinning quantum mechanics provides a consistent and compelling, albeit non-empirical, argument for the existence of multiple universes, continuously challenging our understanding of reality and urging us to explore the profound mysteries hidden within the quantum realm. Cosmic inflation is a pivotal concept in cosmology that dramatically reshapes our understanding of the universe's early moments and potentially sheds light on the existence of other universes. This idea posits that a fraction of a second after the Big Bang, the universe underwent an extremely rapid and exponential expansion. To put it into perspective, within a mere trillionth of a second, the universe's size increased by an inconceivable factor, smoothing out any initial irregularities and setting the stage for the cosmos as we experience it today. This rapid inflationary phase helps explain several crucial cosmological observations. For instance, it accounts for the remarkable uniformity of the cosmic microwave background radiation, the afterglow of the Big Bang, observed across the sky. Despite the seemingly vast distances and the finite speed of light, regions of the cosmos appear remarkably homogeneous. Inflation suggests that these regions were once close together before being thrust apart at unimaginable speeds, hence ironing out any initial disparities. Moreover, inflation isn't limited to our own universe. It naturally extends to the multiverse concept. Certain models of inflation, like eternal inflation, propose that inflation might not have stopped everywhere at once. Instead, while our universe ceased inflating and allowed stars, galaxies, and life to form, other regions might still be inflating, continuously spawning new bubble universes. Each of these bubbles could possess its own unique physical properties, governed by different fundamental constants and laws of physics, potentially harboring entirely different kinds of realities. Thus, cosmic inflation offers a twofold explanatory power. It not only elucidates the observable characteristics and structure of our universe, but also opens the intriguing possibility that our cosmos is just one bubble among an infinite multiverse, each shaped by its own inflationary history. This profound insight broadens our perspective from a singular universe to a potentially infinite expanse of diverse, coexisting realities. The Fermi Paradox is a thought-provoking dilemma that arises from the contrast between the high probability of extraterrestrial civilizations existing elsewhere in the universe and the complete lack of evidence for or contact with such civilizations. Named after the physicist Enrico Fermi, who famously asked, "Where is everybody?" the paradox questions why, given the countless stars and potentially habitable planets, we haven't observed any signs of advanced extraterrestrial life. Several intriguing hypotheses have been proposed to resolve this paradox. One possibility is the rare Earth hypothesis, which suggests that the emergence of complex life is an exceedingly rare event, dependent on a unique combination of astrophysical and geological conditions. This means Earth might be an exceptionally rare cradle of life. Another proposal is the Great Filter Theory, which posits that there are critical stages in the evolution of life that are incredibly unlikely or difficult to pass. This filter could be behind us, like the development of complex cells, or still ahead, like avoiding self-destruction via technological means. The idea of cosmic isolation is another compelling solution. It proposes that advanced civilizations might deliberately avoid contact with others, either to protect themselves from potential threats or to follow a non-interference principle, akin to the prime directive in science fiction. Alternatively, the concept of technological and temporal distance posits that civilizations are either too far apart in space or time for meaningful interaction. They may also communicate using technology beyond our current detection capabilities or in ways we cannot yet comprehend. Finally, some theories entertain the notion that advanced extraterrestrial beings might have already visited Earth or the solar system, but either intentionally or unintentionally left no recognizable trace, or their presence is actively concealed from us, a concept sometimes referred to as the zoo hypothesis. Exploring these solutions not only provides a framework for addressing the Fermi paradox, but also deepens our understanding of life's potential distribution across the cosmos and the myriad factors that could influence the rise and sustainability of advanced civilizations. The theory of panspermia offers a fascinating proposition that life, or at least its fundamental building blocks, could be dispersed throughout the cosmos, hitching rides on comets, asteroids, and other celestial bodies. Instead of life originating independently on each habitable world, panspermia suggests that life might be more like cosmic seeds, traveling across vast interstellar distances to germinate on receptive planets. There are several mechanisms by which panspermia could operate. One form, known as lithopanspermia, posits that life, or prebiotic organic molecules, could be ejected from a planet's surface by massive impacts, such as asteroid collisions, and travel across space embedded within rock fragments. These hardy life forms or molecules could survive the inhospitable conditions of space, eventually crashing onto another planetary body where they might spark the evolution of life. Earth itself could serve as both a donor and recipient in this cosmic exchange. Another variant, radiopanspermia, suggests that microscopic life forms or organic compounds could be propelled through space by radiation pressure from stars. These photons might act like a gentle cosmic wind, pushing microscopic life across interstellar distances. Similarly, comets and asteroids, rich in organic compounds, might repeatedly deliver life's ingredients as they traverse different star systems, potentially introducing prebiotic or even primitive biological material to suitable environments. Panspermia theory isn't solely confined to natural processes. Directed panspermia posits that intelligent civilizations might intentionally seed other worlds with life. This could be driven by a desire to ensure life's continuity or to expand the reach of biological organisms. The possibility of panspermia reshapes our understanding of life's potential universality, suggesting a shared cosmic origin for life across multiple worlds. While we have yet to find definitive evidence supporting panspermia, ongoing research into extremophiles, organisms that thrive in extreme conditions, continues to reveal life's astounding resilience, making the theory a compelling slice of the broader quest to comprehend life's origins. The Great Filter hypothesis provides a sobering perspective on why we have yet to detect extraterrestrial civilizations, addressing the heart of the Fermi Paradox. This hypothesis suggests that there are significant and rare stages or obstacles, referred to as filters, that life must overcome to reach a level of technological advancement capable of interstellar communication and travel. These filters could occur at any point in the evolutionary timeline, from the emergence of life to the development of advanced civilizations. One possibility is that the Great Filter lies behind us, meaning life itself, especially complex, intelligent life, is extraordinarily rare. For example, the transition from simple single-celled organisms to complex multicellular organisms might be an exceedingly improbable event. Similarly, the development of intelligent life capable of creating advanced technology could be another hurdle that few, if any, other forms of life have managed to cross. If such critical stages are indeed rare, it would explain why we appear to be alone in the cosmos. Very few planets, or possibly only Earth, have successfully navigated these challenges. Alternatively, the Great Filter might lie ahead of us, suggesting that while intelligent civilizations may emerge relatively frequently, they almost inevitably encounter insurmountable obstacles that lead to their self-destruction or regression before they can make their presence known to the wider universe. Potential future filters could include catastrophic events such as nuclear war, environmental collapse, pandemics, or even advanced but uncontrollable artificial intelligence driving a civilization to ruin. Another chilling implication is the potential existence of a combination of both past and future filters, implying that the universe is littered with the remnants of civilizations that reached a certain level of technological sophistication only to encounter an insurmountable barrier. This could mean we are approaching our own critical juncture, raising questions about our long-term survivability and urging us to consider more carefully the repercussions of our technological advancements. The Great Filter hypothesis frames the search for extraterrestrial intelligence not just as a question of where and how we might find other civilizations, but also as a poignant reflection on the fragility and unique trajectory of our own progress as a species. It serves as both a warning and a motivation to consider how we navigate our future to ensure we do not become another silent witness to the harsh realities of cosmic evolution. The Theanthropic Principle is a philosophical consideration that suggests our universe appears finely tuned to support life because, simply put, we are here to observe it. This principle comes in two main forms: the weak anthropic principle, WAP, and the strong anthropic principle, SAP, both offering unique perspectives on why the universe's physical constants and conditions seem just right for life. The weak anthropic principle posits that we observe the universe to be life-permitting precisely because only in such a universe could observers like us exist to notice it. It suggests that among a potentially vast number of universes with varying conditions, only those with specific properties could harbor life forms capable of contemplation. Essentially, it's a selection effect. The fact that we are here means that the universe must have the conditions necessary for life's emergence. On the other hand, the strong anthropic principle goes a step further, suggesting that the universe's fine-tuned conditions are not just a coincidence, but might be necessary for the emergence of life. This principle implies that the universe's laws and constants, such as the strengths of fundamental forces, the masses of elementary particles, and the rate of cosmic expansion, might inherently be set to support life. If these conditions were even slightly different, stars, planets, and even complex chemistry necessary for life might not form. This idea of fine-tuning is particularly striking when we consider how delicate some of these balances must be. For example, the strength of the strong nuclear force which binds protons and neutrons in atomic nuclei must be precise. If it were slightly stronger, nuclear reactions in stars would proceed too rapidly, converting hydrogen into heavier elements too quickly. Conversely, if it were weaker, stars might never initiate nuclear fusion, and the universe would lack the essential elements for life. The Theanthropic Principle doesn't necessarily provide a definitive explanation for the universe's fine-tuning, but rather highlights an intriguing correlation between our existence and the cosmos's specific properties. It serves as a thoughtful reminder of our place in the grand scheme of things, nudging us to ponder whether these fine-tuned conditions are a mere cosmic coincidence, a result of a multiverse with diverse properties, or indicative of deeper, possibly intentional cosmic principles. The simulation hypothesis is a provocative idea suggesting that our reality could be an artificial simulation, akin to an extraordinarily sophisticated computer program. Originating from the realms of philosophy and theoretical science, this hypothesis was brought into popular discourse by philosopher Nick Bostrom in the early 2000s. Bostrom's argument is rooted in probability. If civilizations eventually develop the technology to create highly detailed simulations indistinguishable from reality, and if they run numerous such simulations, then it statistically follows that we might be living in one of these simulated realities rather than the base reality. Several arguments underpin the simulation hypothesis. One major argument is the trend of accelerating technological advancement. If we consider the evolution from early computing machines to today's immersive virtual reality, it isn't implausible to imagine a future where technology can simulate conscious beings and entire universes with astonishing detail. Additionally, some physicists have pointed to peculiarities in quantum mechanics and the structure of the universe, such as the discrete nature of space-time at the quantum level, that could be compared to the grid-like nature of pixels in a digital screen, suggesting a programmed reality. Support also comes from considerations of computational power. Given the exponential growth observed in computing capabilities, as described by Moore's law, future civilizations might have the capacity to run simulations containing billions of conscious entities. If even a fraction of such advanced civilizations choose to simulate ancestral histories or experimental realities, the number of simulated realities could vastly outnumber the single physical reality. However, there are counter-arguments and significant skepticism. One key argument against the simulation hypothesis is the sheer scale of computational power that would be required to simulate the entire universe with all its quantum-level details, making the notion impractically ambitious. Critics argue that our understanding of computing might not even encompass the necessary principles to achieve such a vast simulation. Furthermore, there are epistemological challenges. If we're indeed in a simulation, it raises the question of whether we can ever truly know or prove it, given that all our observations and measurements are mediated through the simulated reality itself. It also presents philosophical and ethical dilemmas about the nature of existence and the morality of creating simulated beings capable of experiencing suffering and joy. The simulation hypothesis is a compelling and fascinating speculation, drawing support from technological trends and logical probabilities while facing significant philosophical and practical challenges. Whether factual or philosophical, its implications profoundly impact our understanding of reality, consciousness, and the future of technology, pushing the boundaries of both scientific inquiry and existential contemplation. The Gaia Hypothesis, originally formulated by scientist James Lovelock and microbiologist Lynn Margulis, posits that Earth and its biological systems behave as a single self-regulating organism. It suggests that the interconnectedness of living organisms with their inorganic surroundings creates a synergistic and symbiotic system that maintains conditions conducive to life. Although the Gaia hypothesis primarily applies to Earth, some researchers and philosophers have speculated on its broader implications, extending its principles to the universe as a whole. Extrapolating the Gaia hypothesis to a universal scale essentially leads to the idea of cosmic Gaia, or the notion that the universe itself operates as a self-regulating living entity. This cosmic perspective suggests that just as Earth's biosphere influences and is influenced by geological and atmospheric systems to maintain a state supportive of life, so too might life and the universe reciprocally affect one another. In this view, life isn't just a passive inhabitant of the cosmos, but an active participant in maintaining the conditions of the universe. One way this could manifest is through the role of intelligent life in controlling cosmic processes. For instance, advanced civilizations might actively manage their environments on a planetary or even galactic scale, harnessing energy, stabilizing orbits, or mitigating cosmic threats like asteroid impacts. The potential scope could extend to the manipulation of fundamental constants or even the initiation of processes that create new cosmic structures, akin to terraforming on a grand scale. Furthermore, some proponents suggest that the complexity and emergence of life might influence the universe's trajectory. This could involve concepts like panspermia, where life spreads through the cosmos, perhaps driving evolutionary processes that favor the emergence of more complex life forms. Such a scenario implies a form of cosmic selection, where life not only adapts to the universe, but also plays a role in the ongoing evolution of cosmic habitats. However, this broader application of the Gaia hypothesis remains speculative and faces significant challenges. The universe operates on scales and principles that far exceed our current understanding, and the self-regulating mechanisms observed on Earth may not directly transpose to the cosmos at large. Moreover, the empirical evidence supporting such universal self-regulation is sparse, making it a compelling yet largely theoretical extension. Despite these challenges, extending the Gaia hypothesis to a universal scale opens up profound questions about the interconnectedness of life and the cosmos, the role of intelligent beings in shaping their environments, and the possibility of the universe itself exhibiting characteristics of a living entity. It serves as a thought-provoking framework, encouraging us to consider not only our planet's biosphere, but also our position and responsibilities within the broader cosmic landscape. Dark energy is one of the most enigmatic and profound concepts in cosmology, representing a mysterious force that drives the accelerated expansion of the universe. While it constitutes approximately 70% of the total energy density of the universe, its exact nature remains elusive. Discovered in the late 1990s through observations of distant supernovae, dark energy is now considered a fundamental component of our cosmological model. The role of dark energy in the universe's expansion can be understood through its influence on the fabric of space-time. According to general relativity, matter and energy dictate the curvature and dynamics of space-time. Dark energy, however, appears to have a counterintuitive property. It exerts negative pressure. This negative pressure acts as a kind of repulsive force, driving galaxies apart at an increasing rate. Essentially, while gravity works to pull matter together, dark energy pushes the cosmos apart, overpowering gravitational attraction over large scales. One leading hypothesis to explain dark energy is the cosmological constant, originally introduced by Albert Einstein. He initially proposed it as a term in his equations of general relativity to achieve a static universe, though he later called it his biggest blunder following the discovery of cosmic expansion. Today, the cosmological constant is interpreted as a property of space itself, suggesting that space has an inherent, constant energy density that accelerates expansion. Alternative theories propose varying forms of dark energy, such as quintessence, which envisions dark energy as a dynamic, evolving field, different from the static cosmological constant. This scalar field would change its energy density over time, potentially altering the rate of cosmic expansion. The implications of dark energy are profound and wide-reaching. It affects not only the current state, but also the ultimate fate of the universe. If dark energy continues to drive acceleration indefinitely, we might face a big freeze, where galaxies move so far apart that star formation ceases and the universe becomes dark and cold. Alternatively, if the nature of dark energy changes, it could lead to different end scenarios, including a big rip, where the accelerating expansion tears apart galaxies, stars, and eventually atomic particles themselves. Dark energy is a critical and still largely mysterious element in our understanding of the universe's structure and fate. Its discovery has revolutionized cosmology, pushing us to explore beyond the visible and baryonic matter that constitutes the world we directly observe, and to grapple with the deep underlying mechanisms driving our ever-evolving cosmos. The Big Rip is one of the more dramatic hypotheses for the ultimate fate of the universe, driven by the mysterious force known as dark energy. If dark energy's repulsive force not only remains constant, but actually increases over time, the Big Rip scenario becomes a theoretical possibility. Under this model, dark energy's negative pressure would grow so potent that it would overcome all other forces binding the cosmos together, leading to a cataclysmic dissociation of matter and structure on every scale. To understand the Big Rip, it helps to start with the concept of the cosmological constant and then extend it to more extreme forms of dynamic dark energy. In most conventional models, dark energy is described by the cosmological constant, which assumes a stable energy density per unit volume of space. However, in the Big Rip scenario, dark energy would be represented by a form of phantom energy, characterized by an equation of state with a parameter less than -1. This implies an accelerating force that grows stronger over time. As this phantom energy intensifies, the expansion rate of the universe would accelerate exponentially. Astronomical structures would begin to disintegrate sequentially. Initially, roughly a few billion years before the Big Rip, the gravitational bonds holding galaxy clusters together would be the first to snap. Galaxies themselves would follow, their constituent stars flung apart as their gravitational cohesion is overwhelmed. As the destructive force amplifies, even solar systems would be torn asunder, individual planets severing from their stars. In the final moments, stars and planets wouldn't be the last victims. On a microscopic scale, the same force that disrupts massive celestial bodies would also overcome the electromagnetic forces holding atoms together, leading to the fragmentation of matter at the atomic and subatomic levels. At the crescendo of the Big Rip, all matter would implode into a state of individual, isolated particles, and space-time itself could be stretched to the point of rupture. Although the Big Rip is a speculative and apocalyptic vision, it serves as a valuable theoretical exploration of dark energy's potential effects. It emphasizes the importance of understanding the precise nature and behavior of dark energy, as even small changes in our cosmological models can lead to vastly different predictions for the universe's future. Continuous observations and advanced models strive to narrow down the parameters governing dark energy, helping to determine whether we are heading towards such an extreme fate or a more gradual cosmic end. White holes are a theoretical concept that emerges from the equations of general relativity, originally conceived as the time reversal of black holes. While black holes are regions of space where gravity is so intense that nothing, not even light, can escape once it crosses the event horizon, white holes represent the opposite end of the spectrum. They are hypothetical regions where matter and energy can emerge but nothing can enter, essentially spewing out matter and radiation. The theory behind white holes is intricately linked to the solutions of Einstein's field equations. In the Schwarzschild metric, which describes a non-rotating spherically symmetric black hole, there exists a mathematical solution that is essentially a mirror image of a black hole called a white hole. In this solution, the singularity that pulls matter in, as in a black hole, becomes a singularity from which matter is ejected. This hypothetically connects the two in a manner similar to, but distinctly different from, the concept of a wormhole. White holes, as proposed, are fascinating because they push the boundaries of our understanding and challenge the norms of physics as we know it. For example, while black holes have been extensively studied and observed indirectly through their effects on nearby matter and radiation, there has been no empirical evidence for white holes. This makes them an intriguing but purely theoretical construct at this stage. One of the critical differences between black and white holes lies in their thermodynamic behavior. Black holes, through the process of Hawking radiation, can lose mass and eventually evaporate over astronomical timescales. White holes, by contrast, are theorized to be perpetually expelling matter and energy until they essentially run out of their initial mass-energy content. But their continued existence implies a violation of the second law of thermodynamics, making them less plausible from a thermodynamic standpoint. Furthermore, while black holes play a significant role in astrophysical phenomena, such as the formation of galaxies and the emission of X-rays from accretion disks, white holes have no such observed counterparts. Their very nature proposes scenarios that seem highly unlikely considering the current state and observations of our universe. Some speculative theories and extended frameworks of cosmology, including quantum gravity and certain interpretations of the Big Bang, hint at the possible roles or analogues of white holes, yet these remain at the fringes of mainstream science. While black holes are an essential and well-studied component of our universe, white holes remain hypothetical entities, intriguing in their implications but without observational support. They highlight the fascinating complexity and continuous evolution of theoretical physics, stretching the limits of our understanding and challenging us to explore further. Imagine the universe not as a one-time explosion, but as an eternal rhythm, a cosmic heartbeat that pulses through epochs of creation and destruction. This is the premise of the cyclic universe theory, a profound departure from the traditional Big Bang theory. According to the Big Bang theory, our universe began approximately 13.8 billion years ago from an infinitely dense singularity, expanding and cooling into the cosmos we observe today. However, the cyclic universe suggests something different. It posits that the universe undergoes endless cycles of big bangs, followed by big crunches. In this model, what we perceive as the beginning of time is merely one phase in an infinite sequence of expansions and contractions. The science behind this concept can be as mind-bending as the idea itself. Instead of a single initial explosion, the cyclic model proposes that energy and matter are periodically compressed into a singular point, or big crunch, which then bounces back in another big bang, initiating a new cycle. This continuous loop bypasses the notion of a definitive beginning or end, fundamentally challenging the traditional view of a single linear timeline. Scientists who support this theory draw upon concepts from quantum mechanics and general relativity to suggest that these cycles could prevent the universe from ever reaching a state of total entropy or thermal death. By envisioning time itself as cyclical, the cyclic universe theory redefines our understanding of existence and offers a potentially infinite cosmic history, providing a tantalizing contrast to the finite narrative offered by the traditional Big Bang theory. Kepler 452b, often hailed as Earth's older cousin, orbits a sun-like star about 1,400 light-years away in the constellation Cygnus. Its intrigue lies in its placement within the habitable zone, a sort of cosmic sweet spot where temperatures could allow for liquid water to exist, crucial for life as we know it. Discovered by NASA's Kepler Space Telescope, this exoplanet is about 60% larger in diameter than Earth and lies in an orbit that takes approximately 385 days to complete, remarkably similar to our own yearly cycle. This orbital resemblance suggests that Kepler 452b receives a similar amount of stellar energy as Earth, increasing the odds that its surface could maintain conditions conducive to life. The potential for life on Kepler 452b also stems from its stellar parent. The planet orbits a G-type star, much like our Sun, but slightly older, about 6 billion years. This extra age could offer a longer period for life to potentially develop and evolve. Moreover, the star is only marginally more luminous than our Sun, meaning the radiation levels are akin to what we experience on Earth. Scientists speculate that if Kepler 452b possesses a rocky composition like Earth's, it might have a stable environment where water can remain liquid and where atmospheric conditions could foster biological processes. Although direct evidence of life has yet to be discovered, the similarities in size, orbit, and solar energy input make Kepler 452b one of the most promising candidates in the ongoing quest to find extraterrestrial life. Hot Jupiters are a fascinating class of exoplanets that stand in stark contrast to the gas giants in our own solar system. Unlike Jupiter and Saturn, which orbit relatively far from the Sun, these scorching behemoths huddle extremely close to their parent stars, often within a fraction of the distance between Mercury and the Sun. As a result, their atmospheric temperatures can skyrocket to thousands of degrees Fahrenheit, leading to dramatic and sometimes bizarre atmospheric phenomena. For instance, it is not unusual for hot Jupiters to have winds reaching thousands of miles per hour, and cloud formations composed of strange compounds such as silicates and titanium oxide. This close proximity also means that these planets experience significant tidal forces, often causing them to be tidally locked. That is, one side perpetually faces the star while the other remains in darkness, creating extreme temperature differentials across the planet. Another striking difference between hot Jupiters and our solar system's gas giants lies in their formation and migration patterns. Traditional models of planetary formation suggest that gas giants form in the colder, outer regions of a solar system, where icy materials can accumulate to create a massive core, attracting a thick atmosphere of hydrogen and helium. However, hot Jupiters challenge this model because their current locations within the frost line, the region too warm for ices to solidify, imply they likely formed farther out and migrated inward. This inward migration could be driven by interactions with the protoplanetary disk or gravitational encounters with other planets. These dynamic journeys possibly jostled the exoplanetary systems, disrupting the orbits of smaller rocky planets and leading to a chaotic arrangement unlike the relatively orderly layout of our solar system. Thus, hot Jupiters not only expand our understanding of planetary diversity, but also challenge the traditional narratives of planetary system evolution. Proxima Centauri b captivates the imagination of astronomers and enthusiasts alike due to its position as the closest known exoplanet to Earth, orbiting Proxima Centauri, our nearest stellar neighbor, just over 4.2 light-years away. The planet's significance in the search for extraterrestrial life is multifaceted, starting with its location in the habitable zone, where conditions might allow for liquid water to exist on its surface. Proxima Centauri b is roughly comparable to Earth in size, with a mass about 1.3 times that of our planet, suggesting it could potentially have a rocky composition, a primary consideration for habitability. Proxima Centauri orbits its red dwarf star at a distance much closer than Mercury's orbit around the Sun, completing a full revolution in just 11.2 Earth days. Despite this proximity, the planet receives about 65% of the solar energy Earth gets from the Sun, which makes it an intriguing candidate for habitability. However, red dwarf stars like Proxima Centauri are known for their volatile nature, emitting powerful stellar flares that could strip away a planet's atmosphere if it lacks a strong magnetic field. Thus, Proxima Centauri b serves as an excellent laboratory for studying the potential climatic and atmospheric dynamics of planets orbiting red dwarfs, which are the most common type of star in our galaxy. Its proximity also means that future telescopes and space missions could feasibly send probes or capture more detailed images and data, bringing us closer to determining whether this nearby exoplanet could indeed harbor life. The detection of Proxima Centauri b fuels our curiosity and reinforces the idea that potentially habitable worlds may be much more common and closer than we previously thought, propelling the ongoing search for extraterrestrial life into an exhilarating new phase. Water worlds, also known as ocean planets, are fascinating celestial bodies where a significant portion of their mass is comprised of water. These planets form through a series of complex processes that begin in the protoplanetary disk, the dense cloud of gas and dust that surrounds a newborn star. Within this disk, water-rich, icy bodies from the outer regions can migrate inward or coalesce to form larger planetary embryos, eventually developing into full-fledged water worlds. Unlike Earth, whose surface water is just a thin veneer, water worlds boast deep global oceans that may extend hundreds of miles, covering the entire surface and potentially harboring exotic forms of marine environments. The unique characteristics of water worlds deepen our fascination. For one, the sheer depth of their oceans could create immense pressure at the seafloor, potentially leading to the formation of high-pressure ice phases such as Ice Cephenth or Ice X, states of water ice that exist only under extreme conditions. These oceans are likely devoid of continents or land masses, presenting a stark, continuous aquatic expanse. Depending on their distance from their parent star, these planets could possess a wide range of environmental conditions. If nestled within the habitable zone, the waters of a water world might range from temperate to slightly warm, resembling an enormous version of Earth's oceans. In colder regions further from the star, the surface could be capped with a thick layer of ice, trapping a liquid ocean beneath, akin to the subsurface oceans suspected on moons like Europa and Enceladus in our solar system. Moreover, the pressure and temperature conditions beneath these deep oceans could foster unique chemical environments, potentially supporting forms of life vastly different from what we know. The study of water worlds not only helps to expand our understanding of planetary diversity, but also stimulates our imagination about the myriad ways life might adapt and thrive in environments radically different from our own. This elevates water worlds as compelling targets in the search for extraterrestrial life and our quest to comprehend the myriad expressions of planetary habitability. Super-Earths are a class of exoplanets with masses ranging between 1 and 10 times that of Earth. Their intriguing nature stems from their potential to bridge the gap between the terrestrial planets, like Earth and Mars, and the gas giants, such as Neptune and Jupiter. These planets can vary in composition from rocky, Earth-like structures with thin atmospheres to gas-rich mini-Neptunes with thick envelopes of hydrogen and helium. The diversity inherent in the super-Earth category makes them all the more captivating to astronomers who are keen to understand the various ways planets can form and evolve across the universe. One of the most compelling aspects of super-Earths is that they may possess conditions suitable for life, depending on their location within the habitable zone of their parent star. If a super-Earth orbits at an ideal distance, where temperatures could allow for liquid water to persist on its surface, it significantly raises the prospects for habitability. Additionally, their larger size compared to Earth suggests they might maintain their geological activity and magnetic fields over longer periods. This geologic activity could result in more volcanic outgassing, which helps maintain an atmosphere and could cycle essential nutrients through any bodies of water, promoting biochemical processes crucial for life. Super-Earths also provide a unique opportunity for scientists to test theories of planet formation and migration. The relative abundance of these planets compared to gas giants suggests that their formation might be more common than previously thought, challenging existing models, which once presumed super-Earths to be rare. Furthermore, with technological advancements in telescopes and space missions, astronomers are increasingly able to study the atmospheres of these distant worlds, searching for signatures of water, oxygen, and other biomarkers. Each new discovery of a super-Earth adds a valuable piece to the cosmic puzzle, potentially guiding us closer to identifying habitable worlds beyond our solar system. HD 189733b, an exoplanet located approximately 63 light-years away in the constellation Vulpecula, exhibits some of the most bizarre and hostile weather patterns ever imagined. This hot Jupiter orbits very close to its parent star, which results in surface temperatures soaring to around 1,800 degrees Fahrenheit. Under such extreme conditions, the planet's atmosphere becomes a cauldron of unusual chemistry and violent meteorological phenomena. One of the most fascinating and unsettling discoveries about HD 189733b is that it might experience rainstorms of molten glass propelled by incredible wind speeds. The strange weather on HD 189733b can be attributed to its highly irradiated atmosphere. The intense heat from its star causes the planet's atmospheric gases to undergo complex chemical reactions, creating silicate particles in the upper atmosphere. These tiny glass particles can condense within clouds and then rain down, driven sideways by winds that rage at speeds of up to 4,500 miles per hour. The combination of high temperatures and fierce winds turns the planet into a surreal, hostile environment, where glass rain, instead of falling vertically, would whip horizontally, scouring everything in its path. Additionally, the blue hue of HD 189733b, reminiscent of Earth's color, adds to its fascinating nature but arises from entirely different causes. Rather than oceans and skies, the remarkable color of this exoplanet comes from high-altitude hazes, composed of silicate particles that scatter blue light more effectively than red. These chaotic and extreme weather patterns challenge our understanding of planetary atmospheres and remind us of the diversity of conditions that planets can exhibit. Indeed, exoplanets like HD 189733b broaden our comprehension of the possible atmospheric dynamics and chemistry beyond our solar system, showcasing the rich tapestry of the cosmos. 55 Cancri E, often dubbed the Diamond Planet, fascinates the scientific community due to its extraordinary composition and extreme conditions. This exoplanet orbits its sun-like host star, 55 Cancri A, just 40 light-years away in the constellation Cancer. What sets 55 Cancri E apart is not just its proximity to Earth, but its unique and extreme makeup. It is classified as a super-Earth, with a mass about 8 times that of our planet and roughly twice its diameter. But what truly captures attention is the hypothesis that a significant portion of its mass could be composed of carbon in the form of diamond. The idea of a diamond-rich planet arises from 55 Cancri E's high density and the unusual chemical composition of its host star, which is rich in carbon. Given the intense pressure conditions likely present beneath the planet's crust, it is theorized that substantial amounts of carbon could have crystallized into diamond. Imagine the core of 55 Cancri E as a colossal diamond, a sparkling heart encased in layers of silicate rock. However, definitive evidence for this composition is still pending, and the precise internal structure remains a topic of intense study and debate. Another unique aspect of 55 Cancri E is its extreme surface environment. The planet orbits incredibly close to its star, completing a revolution in just 18 hours. This proximity results in surface temperatures soaring to around 4,000 degrees Fahrenheit on the day side. Observations suggest that the planet might have a molten surface or even lakes of lava, contributing to its otherworldly allure. The night side, while somewhat cooler, remains extremely hot by terrestrial standards. This scorching environment, combined with the planet's carbon-rich hypothesis, paints a picture of a world so alien and extreme that it challenges our conventional understanding of planetary formation and composition. 55 Cancri E not only intrigues due to its potential wealth in diamonds, but also pushes the limits of what we consider possible in planet formation and celestial mechanics. Tidally locked planets present a fascinating and stark contrast to Earth-like planets in terms of climate and habitability. On a tidally locked planet, one side perpetually faces its star while the other remains in darkness. This unique orientation arises because the planet's rotational period matches its orbital period, similar to how the Moon always shows the same face to Earth. This results in extreme and constant dichotomies between the hemispheres. The day side basks in continuous starlight, experiencing permanent daylight and intense heat, while the night side is shrouded in eternal darkness and frigid cold. These conditions create a striking climate disparity, unlike the more uniform variation of temperatures driven by Earth's rotation and axial tilt. The habitability of tidally locked planets hinges on several critical factors. The day side may become scorching hot, potentially exceeding temperatures that would allow for liquid water to exist, while the night side could plummet to sub-freezing temperatures. However, a habitable twilight zone or terminator, the region around the planet's circumference where the day and night sides meet, might exist where conditions are more moderate. If the planet possesses a thick, stable atmosphere, heat could be redistributed from the day side to the night side through atmospheric circulation, potentially moderating the extreme temperatures and making the terminator region more hospitable. Oceans and atmospheres, if present, can also transport heat across the planet, creating a balance that might enable life to thrive in certain areas. Additionally, the composition and behavior of the atmosphere play a crucial role. On a tidally locked planet orbiting a red dwarf star, for instance, stellar flares and high-energy radiation could strip away the atmosphere if there is no magnetic field to protect it. However, if the atmosphere remains intact and heat distribution is efficient, such planets could provide stable environments conducive to life. The theoretical models and emerging data on tidally locked exoplanets thus expand our understanding of habitability beyond the traditional Earth analog. Studying these worlds helps scientists explore the diverse conditions under which life could arise and persist, fundamentally broadening the scope of our search for extraterrestrial life. Rogue planets drifting through the galaxy without a parent star present an enigmatic and intriguing component of our cosmic neighborhood. Unlike typical planets that orbit stars, rogue planets wander the interstellar voids, largely devoid of sunlight or heat from a stellar companion. Their origins remain a topic of scientific investigation, but many astronomers believe that they could have been ejected from their parent systems due to gravitational interactions with other planets or passing stars. This ejection could happen during the volatile periods of planetary formation when bodies jostle for stable orbits, sending some planets hurtling into interstellar space. The role of rogue planets in the galaxy is multifaceted. They provide valuable insights into the dynamics of planetary systems, revealing the chaotic processes that can strip a planet from its star. Moreover, rogue planets challenge our understanding of what constitutes a habitable environment. Unlike Earth, which relies on solar radiation, a rogue planet could potentially harbor life sustained by other forms of energy. For instance, internal heat generated by radioactive decay or tidal forces from hypothetical moons could create subsurface oceans beneath thick ice layers, offering a potential refuge for life forms. These unique conditions force scientists to rethink the criteria for habitability and the diverse environments where life might exist. Detecting rogue planets is a profound challenge due to their lack of luminous stars to backlight them. Traditional methods like the transit technique used for exoplanets around stars are not applicable. Instead, astronomers often rely on gravitational microlensing, a phenomenon predicted by Einstein's theory of general relativity. When a rogue planet passes in front of a distant star, its gravitational field acts as a lens, temporarily magnifying the light from that star. This brief lensing event can reveal the presence of the rogue planet. Additionally, direct imaging might capture larger rogue planets emitting their own faint infrared glow, especially when they are relatively young and still warm from their formation. These detection methods, though complex and requiring precise alignment, continue to unveil the hidden population of rogue planets, enriching our understanding of the galaxy's planetary diversity. Detecting planets in the habitable zones of distant stars involves a combination of sophisticated techniques and advanced technology, aimed at finding the delicate balance where conditions might allow for liquid water, a key ingredient for life as we know it. One of the most effective methods is the transit method, employed by missions like NASA's Kepler Space Telescope. This technique involves continuously monitoring the brightness of numerous stars to spot periodic dips in light levels. These dips occur when a planet crosses or transits in front of its host star from our line of sight. By analyzing the frequency, duration, and depth of these transits, scientists can infer not only the presence of a planet, but also estimate its size and orbital period. When a planet's orbit places it within the star's habitable zone, it becomes a prime candidate for further study. Alongside the transit method, the radial velocity technique, or Doppler spectroscopy, offers another powerful tool. By observing the star's spectrum, scientists can detect minute wobbles in the star's motion caused by the gravitational pull of an orbiting planet. As a planet orbits, it exerts a small but detectable influence on its star, causing the star to shift slightly in position. This movement alters the wavelengths of the star's light, making them appear periodically red-shifted and blue-shifted. Analysis of these shifts allows astronomers to determine the planet's mass and orbit, providing critical details about whether the planet resides in the habitable zone. Additionally, direct imaging is gaining traction as technology advances, although it's significantly challenging due to the glare of the parent star. Instruments like the Hubble Space Telescope and ground-based observatories using adaptive optics have begun to capture images of exoplanets by blocking out the star's light, revealing the planets themselves. Finally, gravitational microlensing also plays a vital role in discovering distant planets, including those in the habitable zones. When a massive object passes in front of a star, it bends the light in a way that can reveal the presence of planets around the intervening object. Each method has its strengths and limitations, often working best in combination. For instance, transit observations can be confirmed and supplemented with radial velocity data, allowing for precise characterizations. Collectively, these methods have led to the discovery of thousands of exoplanets, some of which tantalizingly lie within their stars' habitable zones, sparking renewed interest in the possibilities of finding life beyond Earth. A zombie galaxy is a poignant term describing galaxies that have stopped creating new stars, entering a state of what's metaphorically considered cosmic death. Unlike galaxies like our Milky Way, which continue to convert interstellar gas into new stars, zombie galaxies exhibit a cessation in star formation, leading to their gradual dimming over cosmic timescales. These galaxies earned their moniker because although they still exist and possess old stars, They lack the vibrant, energetic processes associated with stellar birth, giving them an eerie, lifeless quality, much like zombies. One of the defining characteristics of zombie galaxies is their depleted reservoir of cold gas, the essential raw material for star formation. Several processes can contribute to this depletion. For instance, interactions and collisions with other galaxies can strip away their gas, a phenomenon known as ram pressure stripping. Additionally, intense periods of star formation in the past, known as starbursts, can exhaust these galaxies' gas supplies, or energetic events like supernovae and active galactic nuclei can heat the remaining gas, making it incapable of condensing into new stars. This thermal feedback prevents the gas from cooling down, compressing, and forming new stellar generations, effectively halting the galaxy's evolutionary process. Zombie galaxies often populate dense regions of the universe, such as galaxy clusters, where gravitational forces and intergalactic conditions expedite the stripping away of gas. These galaxies are typically older and redder than their star-forming counterparts. The red coloration comes from the population of older, cooler stars that dominate their stellar composition, as young, hot blue stars are no longer being formed. Examples of zombie galaxies include many elliptical and lenticular galaxies, which show little to no ongoing star formation activity. The study of zombie galaxies provides critical insights into the life cycles of galaxies and the factors influencing galactic evolution. By understanding why and how these galaxies cease their star-forming activities, scientists can piece together the broader narrative of cosmic development, shedding light on the intricate interplay of processes that shape our universe. Starburst galaxies earn their title thanks to their prodigious ability to produce stars at rates far exceeding those of ordinary galaxies. This exceptional star formation can be several hundred times greater than what occurs in a typical galaxy like the Milky Way. But what drives this stellar frenzy? The key lies in the abundance of gas and the dynamic, often chaotic environments in which these galaxies reside. One of the primary catalysts for a starburst galaxy is a galactic collision or close encounter. When galaxies interact, their gravitational forces can compress vast clouds of gas, triggering the collapse that leads to star formation. This galactic crash course shoves the gas into dense regions where it cools and fragments into clumps, each of which can give birth to new stars. As these processes unfold, the collisions also stir up turbulent flows within the interstellar medium, further encouraging the rapid transformation of gas into stars. Another contributing factor involves the inflow of fresh gas. Starburst galaxies often possess mechanisms that channel cold gas efficiently into their central regions, replenishing the material needed for new star formation. This can happen through streams of intergalactic gas or by drawing reserves from the outskirts of the galaxy towards the center. Such inflows maintain a steady supply of star-making material, allowing the starburst phase to sustain itself for extended periods, typically a few 100 million years. The intense activity in a starburst galaxy isn't without consequence. The formation of large numbers of massive stars leads to significant energy outputs in the form of ultraviolet radiation, stellar winds, and supernova explosions. These highly energetic processes can impact the surrounding environment drastically, sometimes driving gas out of the galaxy or heating it to temperatures where it can no longer cool and condense into new stars. Paradoxically, while these feedback mechanisms might eventually quench the starburst, during their peak they contribute to the rich, complex interplay of forces that define these vibrant galactic phases. Thus, starburst galaxies are vivid laboratories of star formation, displaying cosmic fireworks that help astronomers understand the life cycle of galaxies. The intense periods of star production provide critical clues about the processes that can fuel rapid growth in galaxies, painting a dynamic picture of cosmic evolution. The Andromeda Galaxy, also known as M31, holds significant importance in relation to the Milky Way for several reasons. As the nearest spiral galaxy to our own, located about 2.5 million light-years away, Andromeda provides a valuable benchmark for studying galactic structures, formation, and evolution in comparative detail. Its proximity allows astronomers to observe its features more clearly than more distant galaxies, offering insights into the similarities and differences between these two giant spiral galaxies. One of the most profound connections between the Andromeda Galaxy and the Milky Way is their impending collision. Current measurements indicate that Andromeda is hurtling towards us at roughly 110 kilometers per second, suggesting that the two galaxies are on a collision course set to culminate in approximately 4 billion years. This future cosmic event, often referred to as the Great Collision or Milkomeda, will significantly reshape both galaxies. Instead of a cataclysmic smash, this galactic dance will likely be a slow, intricate merging process dominated by gravitational interactions. While individual stars in each galaxy are so far apart that direct stellar collisions will be rare, their mutual gravitational influence will shred and warp the galaxy's structures, eventually leading to the formation of a new, larger elliptical galaxy. Besides this dramatic future, the Andromeda Galaxy's relationship to the Milky Way provides critical insights into the dynamics of the local group, the galaxy cluster that includes both Andromeda and the Milky Way, along with dozens of smaller galaxies. Understanding Andromeda's mass, dark matter halo, and satellite galaxies helps astronomers piece together the history and fate of our local cosmic neighborhood. For instance, studying the dark matter distribution in Andromeda offers clues to the unseen mass that governs the kinematics and evolution of the local group. The Andromeda Galaxy is our closest galactic neighbor and an essential object of study for understanding not only the present state of our cosmic surroundings, but also their dynamic and evolving future. Its looming merger with the Milky Way represents a major event in the story of our galaxy, holding implications for the structure, star formation, and ultimate fate of the stellar populations within. Ring galaxies with their evocative circular structures captivate both professional astronomers and the public alike. These unusual galaxies are characterized by a prominent ring of stars, gas, and dust encircling a sparsely populated or nearly empty core, giving them a strikingly distinct appearance when viewed through telescopes. But how do such peculiar formations come to exist? The formation of ring galaxies is primarily attributed to head-on collisions or near collisions between galactic bodies. When a smaller galaxy, or in some cases a dense galactic core such as a compact star cluster, passes through the center of a larger disk galaxy, gravitational forces trigger intense waves of density compressions in the disk of the larger galaxy. This gravitational disturbance propagates outward like ripples in a pond, compressing interstellar gas and triggering bursts of star formation along the wavefront, which manifests as a prominent ring. The classic example of such ring galaxies is the Cartwheel Galaxy, located about 500 million light-years away in the constellation Sculptor. Its distinctive ring was likely formed by this very process. Ring galaxies are visually striking not only due to their unusual structure, but also because of the brilliant young stars that populate their rings. These stars are typically massive and hot, emitting strong ultraviolet radiation and giving the ring a bright, luminous appearance. The contrast between the bright, star-forming ring and the relatively empty or dimmer central region adds to their captivating visual appeal. Moreover, the interplay of shadows, light, and different colors from young blue stars and older, redder stars can create a rich tapestry of visual textures. In some cases, ring galaxies can also feature secondary or inner rings, adding to their complexity and beauty. The ongoing study of these celestial objects helps astronomers understand the dynamic processes and gravitational interactions that shape galaxy evolution. By examining ring galaxies, researchers gain valuable insights into the fate of interstellar gas, the mechanisms of star formation, and the cosmic timelines required for such structures to form and eventually dissipate. Imagine peering into the night sky and contemplating the boundless expanse of stars, galaxies, and cosmic phenomena. What if I told you that the glimmering stars and glowing nebulae only scratch the surface of what actually shapes the universe? Enter dark matter, a mysterious and invisible substance that fundamentally influences the formation and structure of galaxies. Though dark matter does not emit, absorb, or reflect light, it exerts a gravitational pull that is essential for the cohesion of galaxies. Scientists estimate that dark matter makes up about 85% of the total matter in the universe. Without this unseen yet immensely influential material, galaxies as we know them might not even exist. In the early universe, shortly after the Big Bang, dark matter played a pivotal role in the emergence of the first galactic structures. As the universe cooled and expanded, tiny fluctuations in the density of dark matter began to grow, driven by gravitational forces. These fluctuations acted as the scaffolding upon which ordinary matter, the stuff that stars and planets are made of, began to clump together. Over billions of years, these regions of concentrated dark matter attracted more and more ordinary matter, eventually forming galaxies. The gravitational pull of dark matter continues to glue these cosmic structures together, ensuring that galaxies rotate faster than they would if only visible matter were present. This enigmatic substance not only serves as the cosmic web holding galaxies in place, but also hints at the larger, unseen framework of our universe. At the heart of nearly every large galaxy lies a supermassive black hole, a cosmic titan with masses ranging from millions to billions of times that of our Sun. These gravitational behemoths exert enormous influence on the dynamics of their host galaxies, far beyond the regions immediately surrounding them. Despite being relatively small in physical size compared to the galaxy itself, their pervasive gravitational pull orchestrates the movement of stars, gas, and other matter within the galactic core. As stars and gas clouds orbit the supermassive black hole, their paths are shaped by its incredible gravity, creating a dynamic, often chaotic environment at the galactic center. But the influence of supermassive black holes extends even further. When matter falls into a supermassive black hole, it can form an accretion disk, rapidly heating up and emitting powerful jets of energy. These energetic jets can spew vast amounts of radiation and high-speed particles far into the galaxy and beyond. This process, known as feedback, can have dramatic effects on the host galaxy. For example, the intense radiation can heat up the surrounding gas, preventing it from cooling and collapsing to form new stars, thereby regulating star formation. Additionally, the jets can expel gas from the central regions of the galaxy, further stifling star formation and altering the galaxy's evolution. This dual role, shepherding the motions of stars while simultaneously regulating the raw materials for new stars, places supermassive black holes as central architects in the life cycle of galaxies. Imagine a galaxy so large it could swallow not just thousands, but hundreds of thousands of galaxies like our Milky Way. This colossal entity is IC 1101, a behemoth residing over 1 billion light-years away in the constellation Serpens. With a diameter stretching around 6 million light-years, IC 1101 is one of the largest known galaxies in the universe. The sheer scale of IC 1101 is staggering. It's not just a collection of stars, gas, and dust, it is practically a cosmic metropolis. Scientists believe its enormous size is partly due to its location at the center of a densely populated galaxy cluster called Abell 2029. The gravitational interactions within the cluster catalyze a process known as galactic cannibalism, where IC 1101 has absorbed smaller galaxies over billions of years, leading to its monstrous growth. Besides its gargantuan size, IC 1101's notable features include an immense number of stars, estimated at 100 trillion, as well as an extended halo of old red stars that shine with a faint but collective glow. The galaxy also boasts an enormous central black hole, acting as both a stabilizing anchor and a dynamic influencer in its evolutionary journey. It is suggested that the intense gravitational forces exerted by IC 1101 and its central black hole continue to pull in more material from its surrounding environment, feeding its growth. This continual accumulation of cosmic matter not only extends IC 1101's reach, but also contributes to its complex structure and richness. Unlike typical spiral or elliptical galaxies, IC 1101 exhibits properties of a supergiant elliptical galaxy with little ongoing star formation, signaling a matured yet still evolving galactic giant. Often overshadowed by their larger, more luminous counterparts, dwarf galaxies are cosmic underdogs that punch above their weight in the realm of galactic evolution. These diminutive galaxies, containing as few as 100 million stars, are fundamental to unraveling the complex tapestry of the universe's history. Unlike massive spiral or elliptical galaxies, dwarf galaxies offer a more pristine look at the early universe. Many of them are relatively untouched since their formation, serving as galactic time capsules brimming with ancient stars and primordial gas. This makes them ideal testing grounds for astronomers studying the conditions of the universe just after the Big Bang. Moreover, Dwarf galaxies play a crucial role in the growth of larger galaxies through a process known as hierarchical merging. Over billions of years, gravitational forces cause these small galaxies to coalesce and merge into more massive systems. The Milky Way, for instance, has consumed numerous dwarf galaxies in its lifetime, and this process continues even today. These interactions often trigger new bursts of star formation and can profoundly alter a galaxy's structure and star population. Additionally, dwarf galaxies are often rich in dark matter, providing key data points for understanding its mysterious role in the cosmos. Observations and simulations involving dwarf galaxies help astrophysicists refine their models of dark matter distribution, contributing to broader theories about the fabric of the universe. Diving into the depths of these smaller galaxies also offers insights into galactic environments and phenomena like supernova rates and cosmic ray propagation. Dwarf galaxies act as building blocks and laboratories, illuminating the multifaceted processes that steer the evolution of galaxies on both grand and granular scales. Their study stitches together the narrative of cosmic growth and imparts valuable clues about the underlying mechanisms that have shaped galaxies from the universe's infancy to its present-day complexity. Picture the serene dance of celestial bodies disrupted occasionally by a cosmic ballet of grand proportions, galactic collisions. These interactions occur when galaxies gravitationally attract each other, leading to a slow-motion fusion that can span over billions of years. Despite the seemingly chaotic notion of immense star systems colliding, the vast distances between individual stars mean that direct star-to-star collisions are exceedingly rare. Instead, the encounter triggers a dynamic cascade of events that radically alters the galaxies involved. As galaxies draw closer, their mutual gravitational forces distort their shapes, stretching and twisting their forms into elongated tidal tails and sweeping arcs. The gas clouds within these galaxies often experience more direct confrontations, compressing under the immense gravitational pressure and igniting bursts of intense star formation, a phenomenon aptly termed starburst. During this turbulent phase, supermassive black holes at the centers of the colliding galaxies may also become more active, accreting material at an accelerated rate and emitting powerful jets of energy, further influencing the galactic environment. Eventually, this cosmic choreography culminates in the merger of the two galaxies into a single, more massive galaxy. The resulting entity often bears little resemblance to its progenitors. Elliptical galaxies, characterized by their smooth, featureless light distribution, are commonly formed from such mergers, especially when spiral galaxies are involved. Additionally, the combined gravitational fields can lead to the relaxation of stellar orbits and the redistribution of dark matter, further solidifying the new galaxy's structure. Through these dramatic and often violent unions, galactic collisions drive the evolution and diversity of galaxies, shaping the cosmos in a continuous cycle of creation and transformation. Irregular galaxies, as their name suggests, stand apart as the nonconformists in the galactic family, defying the structured elegance seen in the more common spiral and elliptical galaxies. These galaxies lack the distinct shapes that characterize their siblings. Unlike the majestic spirals with their gracefully curving arms or the smooth, rounded profiles of ellipticals, irregular galaxies often present a chaotic, asymmetrical appearance. This irregularity is usually a sign of past disruptions, such as gravitational interactions with other galaxies or the internal dynamics of young, hot stars stirring the galactic pot. One of the most striking differences is their stellar composition and distribution. Irregular galaxies often harbor large amounts of gas and dust, making them fertile grounds for star formation. This abundance of raw material can give them a patchwork look, with bright regions of young blue stars interspersed with darker, more obscured areas. Compared to the older, more stable star populations found in elliptical galaxies, or the organized mixed-age stars in spirals, irregular galaxies are vibrant and dynamic, but lack the cohesive structure. Irregular galaxies also play crucial roles in the cosmic landscape, particularly concerning galactic evolution. Often, small and medium-sized irregular galaxies are remnants or survivors of more violent past interactions that either haven't yet settled into stable forms or which have been perpetually kept in a state of disruption. Studying these galaxies offers insights into different evolutionary pathways and processes, such as starburst activity, supernova rates, and the effects of gravitational encounters. In their diversity and irregularity, these galaxies offer a living laboratory for astronomers to explore the influences that shape galactic development across the universe. Imagine taking a time machine back nearly 14 billion years to the dawn of the universe, just some 380,000 years after the Big Bang. The afterglow of this primal fireball, known as the cosmic microwave background radiation, or CMB, is an omnipresent relic that fills the cosmos. Discovered accidentally by Arno Penzias and Robert Wilson in 1965, the CMB is a faint, uniform glow that permeates the entire sky, serving as a snapshot of the universe in its infancy. Emitting a spectrum that peaks in the microwave range, this radiation provides a treasure trove of information about the nascent stages of the universe, a period when the cosmos cooled sufficiently for protons and electrons to combine and form neutral hydrogen atoms, allowing light to travel freely for the first time. What makes the CMB particularly fascinating is the subtle irregularities or fluctuations in its temperature, observed at a scale of mere millionths of a degree. These tiny variations are like cosmic fingerprints, revealing the seeds of all future structure, galaxies, stars, and planetary systems. By meticulously analyzing these fluctuations, scientists can infer critical properties of the universe, including its age, composition, and rate of expansion. The pattern of these temperature variations also lends robust support to the Big Bang theory and the concept of cosmological inflation, a rapid expansion that occurred fractions of a second after the Big Bang. However, the CMB holds even deeper mysteries. One perplexing feature is the so-called cold spot, an unusually large and cold region that significantly deviates from the otherwise smooth temperature distribution. Some theories suggest this might be evidence of exotic phenomena, like a supervoid or even a hint of collisions with other universes in a multiverse scenario. Additionally, the precise nature of the dark matter and dark energy, which account for about 95% of the universe's total energy density, remains elusive. Continued study of the CMB, especially with high-precision instruments, promises to illuminate these and other cosmic enigmas, potentially unlocking profound insights into the fundamental nature of reality itself. Envision a cosmic lighthouse beaming forth the most powerful signals in the universe, gamma-ray bursts, GRBs. These extraordinarily intense bursts of gamma radiation can release more energy in a few seconds than our sun will emit over its entire 10 billion-year lifespan. First detected by satellites in the late 1960s, GRBs were initially a complete enigma. These explosive events challenge our understanding of cosmic phenomena by demonstrating the universe's staggering capacity for violence and luminosity. There are two main types of GRBs, short and long, and each tells a different story. Long-duration GRBs, lasting more than 2 seconds, are generally linked to the catastrophic collapse of massive stars into black holes. This stellar death throw, known as a hypernova or collapsar, triggers an immense explosion that blasts gamma rays across the cosmos. Short-duration GRBs, on the other hand, are thought to originate from the merger of compact objects such as neutron stars or neutron stars merging with black holes. These collisions launch relativistic jets at nearly the speed of light, creating the brief yet intensely powerful gamma ray emission. Both types of GRBs offer a glimpse into the most extreme conditions of gravity, density, and magnetic fields, stretching our current astrophysical models to their limits. The far-reaching implications of GRBs extend beyond their immediate, dazzling displays. GRBs serve as cosmic beacons, providing insights into the distant reaches of the universe and offering clues about the rate of star formation and the evolution of galaxies. Their extraordinary brightness allows astronomers to probe environments billions of light-years away, essentially opening a window to observe the universe as it was in its very youth. However, these violent events also pose questions about the survivability of life in the universe. A GRB occurring close enough to Earth could potentially devastate its atmosphere, leading to mass extinctions. The unfathomable power, origin, and aftermath of gamma-ray bursts continue to challenge and refine our understanding of astrophysics and cosmology, showing us that the universe still holds many secrets waiting to be unraveled. Picture a brief enigmatic signal from the cosmos, a sudden split-second flash of radio waves. These are fast radio bursts, or FRBs, and they have been one of the most perplexing astronomical phenomena since their discovery in 2007. Unlike the sustained emissions we often observe from other cosmic sources, FRBs last only milliseconds, but can contain as much energy as the sun emits in an entire day. Capturing these fleeting signals is akin to catching a lightning bolt in a bottle, making their study a true scientific challenge. The origins of FRBs are shrouded in mystery, partly because they are difficult to localize. Initially, their transient nature and unpredictability made it hard for astronomers to determine their sources. With advancements in technology and the development of instruments like the Canadian Hydrogen Intensity Mapping Experiment, CHIME, scientists have pinpointed a few repeating FRBs, allowing for more detailed study. The sources of these bursts vary widely in distance, with some situated billions of light-years away, indicating they come from extraordinarily energetic and cataclysmic events. What makes FRBs so difficult to explain is their sheer diversity and the extreme conditions likely required to generate them. Theories abound, ranging from rotating neutron stars, or magnetars, which have immensely strong magnetic fields, to more exotic possibilities like the activity of alien civilizations. Signal analysis often reveals dispersion, a spread of frequencies arriving at different times, suggesting that these bursts traverse vast cosmic distances and different media, yet the exact mechanisms behind their generation remain speculative. Further complicating the puzzle, some FRBs are one-off events, while others are repeaters, hinting at potentially different origins or processes. The study of FRBs is a fast-evolving field, and each new detection adds another piece to a puzzle that could lead to groundbreaking revelations about the universe's most energetic and mysterious events. Visualize the universe as a vast, malleable sheet, a fabric we call space-time. Now imagine this fabric being gently warped and rippled by moving masses, much like the surface of a pond disturbed by a tossed pebble. These ripples are gravitational waves, disturbances in space-time predicted by Albert Einstein in 1915 as part of his general theory of relativity. It wasn't until a century later in 2015 that the Laser Interferometer Gravitational Wave Observatory, LIGO, made the groundbreaking first detection of these waves, emanating from the collision of two black holes over 1 billion light-years away. Gravitational waves offer an entirely new way to observe and understand the universe, providing insights that are impossible to glean from traditional electromagnetic telescopes. When cataclysmic events such as black hole mergers or neutron star collisions occur, they create powerful gravitational waves that travel through space-time, carrying information about their origins. By detecting and analyzing these waves, scientists can infer critical characteristics of these extraordinary events, such as the masses, spins, and distances of the objects involved. Unlike light, which can be obscured or altered by interstellar matter, gravitational waves travel unimpeded, offering a pristine view of these cosmic phenomena. Beyond revealing the dynamics of extreme astrophysical events, gravitational waves are pivotal for probing the fundamental nature of space-time itself. They serve as a tool for testing the limits of general relativity under the most extreme conditions, far beyond what can be achieved within our solar system. These waves may also expose new exotic phenomena, such as hypothetical entities like primordial black holes, or even clues about the state of the universe moments after the Big Bang. As the sensitivity of gravitational wave detectors continues to improve and new observatories like the European Space Agency's LISA aim for space-based detection, the study of gravitational waves promises to revolutionize our understanding of the cosmos, revealing the intricate dance of matter and energy that shapes space-time. The cold spot in the cosmic microwave background, CMB, is one of the most intriguing and enigmatic features in our observations of the universe's infancy. Found in the southern constellation of Eridanus, this region is noticeably colder by about 70 microkelvin than the surrounding areas of the CMB. Discovered by the Wilkinson Microwave Anisotropy Probe, WMAP, and later confirmed by the Planck satellite, the cold spot stands out as a significant anomaly in the otherwise remarkably uniform temperature distribution of the CMB. Its existence challenges the standard cosmological model and has led to a plethora of theories attempting to explain its origin. One leading theory posits that the cold spot could be the result of a massive void, or supervoid, along the line of sight between us and the CMB. A supervoid is an enormous underdense region of space containing far fewer galaxies and matter than average. If such a void exists, photons traveling through it could lose energy due to the integrated Sachs-Wolf effect, where the expanding universe causes the gravitational potential to change as photons traverse the void. This effect could stretch the light waves, resulting in a cooler temperature observed in that particular patch of the sky. Another fascinating yet speculative theory is the idea of the cold spot being a signal from beyond our observable universe. Some scientists suggest it could be an imprint of a collision with another universe in a multiverse scenario. Such an encounter would leave a detectable mark on the CMB, manifesting as an anomaly like the cold spot. Although highly speculative and currently lacking direct evidence, the multiverse hypothesis keeps the door open for unconventional explanations that challenge our understanding of cosmology. Yet another possibility is that the cold spot is simply a statistical fluke, a rare fluctuation that appears significant but falls within the realm of expected variations in the CMB. While unlikely this explanation adheres to the principles of random distribution and cosmic variance, the limits to how closely measurements of the CMB will conform to theoretical predictions purely due to chance. Regardless of the explanation, the cold spot remains a focal point for ongoing research and debate. As scientists continue to gather more precise data and develop advanced models, they hope to unravel the mysteries surrounding this peculiar feature, potentially leading to groundbreaking discoveries about the nature of our universe. Within the grand architecture of the cosmos, voids and supervoids are the expansive, cavernous regions that contrast with the dense, clustered tapestry of galaxies and galaxy clusters. These vast, underpopulated areas can span tens to hundreds of millions of light-years, forming a critical element of the large-scale structure of the universe. While voids may seem like the empty spaces in the cosmic web, their presence and properties significantly influence the evolution and distribution of matter throughout the universe. Voids and supervoids shape the large-scale structure by defining the boundaries between the dense filaments and clusters. As galaxies and dark matter gather under gravity to form these structures, the remaining space becomes more tenuous, leading to the formation of voids. These gaps are not entirely devoid of matter, but contain significantly fewer galaxies compared to their denser counterparts. The distribution and size of voids contribute to our understanding of the overall geometry and expansion rate of the universe, offering a counterbalance to the clumping tendencies of matter. Moreover, voids provide unique laboratories for cosmologists probing the fundamental properties of the universe. For instance, the study of voids helps refine models of dark energy, the mysterious force driving the accelerated expansion of the universe. Because voids are regions of lower gravitational potential, they offer a clearer view of dark energy's effects on cosmic expansion, unencumbered by the complex gravitational interactions present in denser regions. By measuring how voids expand over time, scientists can gain insights into the nature of dark energy and test predictions of the current cosmological models. Supervoids, being even larger and more significant, can offer a deeper understanding of cosmic phenomena. They impact the cosmic microwave background via the integrated Sachs-Wolf effect, causing subtle temperature variations that provide clues about the early universe's conditions and the overall matter distribution. Additionally, voids and supervoids influence the motion of galaxies on large scales, contributing to peculiar velocities that can affect gravitational lensing and the anisotropies observed in the CMB. These emptier regions of the universe thus hold some of the keys to comprehending the cosmic tapestry's vastness and complexity. By studying voids and supervoids, scientists can unravel the interplay between matter and dark energy, bridging gaps in our understanding of cosmological principles and the underlying structure shaping our universe. The Hubble constant, named after the renowned astronomer Edwin Hubble, is a critical parameter in cosmology that quantifies the rate at which the universe is expanding. Expressed as the rate at which galaxies recede from each other per unit distance, the Hubble constant essentially gives us the current speed of cosmic expansion. Understanding this rate is of profound importance because it allows scientists to make far-reaching inferences about the age, size, and future behavior of the universe. The significance of the Hubble constant extends into several fundamental areas of cosmology. First and foremost, it helps determine the age of the universe. By measuring the current rate of expansion, astronomers can extrapolate backward to infer when the Big Bang occurred. A precise value also aids in refining our models of the universe's overall structure, offering insights into the interplay between dark matter, dark energy, and ordinary matter. Furthermore, the Hubble constant assists in calibrating the distance scale of the universe, enabling accurate measurements of distances to far-off galaxies and improving our understanding of cosmic phenomena. Despite its pivotal role, the exact value of the Hubble constant has become one of the most contentious issues in contemporary astrophysics. Different methods of measurement have resulted in significantly divergent values, leading to what is often referred to as the Hubble tension. Traditional methods such as observing Cepheid variable stars and type Ia supernovae in nearby galaxies yield one value. These objects serve as standard candles due to their well-known luminosities, allowing astronomers to derive the expansion rate. This method has given us a Hubble constant value of around 74 kilometers per second per megaparsec. On the other hand, measurements based on the cosmic microwave background, CMB radiation, specifically from the Planck satellite, offer a different value, approximately 67 kilometers per second per megaparsec. This method involves observing the residual heat from the Big Bang and fitting the data to a cosmological model known as the Lambda CDM model, which integrates dark matter and dark energy components. The discrepancy between these two methods has not only persisted, but become more pronounced with increasingly precise data, fueling debates among cosmologists. The resolution of this tension could lead to either a refinement of measurement techniques or a groundbreaking revision of our cosmological models. If the current models are correct, then unknown systematic errors might be skewing the results. Alternatively, new physics beyond the standard model of cosmology might be at play, perhaps involving intricacies in dark energy, modifications to general relativity, or other exotic phenomena. Thus, the quest for the exact value of the Hubble constant remains a frontier of scientific investigation, holding the potential to revolutionize our understanding of the universe. When you peer into the night sky, the light from distant galaxies carries more than just the image of shimmering stars. It holds a cosmic fingerprint of the universe's history. One of the most telling features of this light is its redshift, a phenomenon where the wavelengths of light are stretched to longer, redder wavelengths as galaxies recede from us. This shift toward the red end of the spectrum is a direct consequence of the universe's expansion, a discovery that has been pivotal in our understanding of cosmology. The concept of redshift is grounded in the Doppler effect, which we encounter in everyday life when the pitch of a siren changes as an ambulance passes by. For galaxies, a similar effect is observed. As they move away from us, the light they emit is stretched, lengthening the wavelengths and shifting the light toward the red part of the spectrum. Astronomers measure this redshift to determine how fast a galaxy is receding. The degree of redshift allows them to calculate the velocity of the galaxy relative to Earth. By systematically measuring the redshifts of numerous galaxies, astronomers can plot these velocities against their distances, leading to a profound revelation. This relationship was first articulated in the 1920s by Edwin Hubble, who observed that more distant galaxies are receding faster, a hallmark of an expanding universe. This correlation, now known as Hubble's law, is typically expressed as a straightforward formula. Velocity equals Hubble's constant multiplied by distance. Redshift not only acts as a cosmic speedometer but also as a time machine. Because light from distant galaxies takes billions of years to reach us, observing redshifted light is akin to looking back in time. The greater the redshift, the further back we can glimpse into the history of the universe. For instance, quasars and other luminous objects with extreme redshifts show us what the universe was like in its early stages, often revealing details about the formation of galaxies, stars, and even the evolution of cosmic structures. Furthermore, redshift measurements have been crucial in the discovery and understanding of dark energy. Observations of distant supernovae, which act as standard candles due to their known luminosities, have shown that the expansion of the universe is accelerating. This acceleration implies the presence of dark energy, a mysterious force that permeates space. Redshift serves as a fundamental tool for astronomers, allowing them to measure and map the expansion of the universe, gain insights into its age and structure, and explore the nature of dark energy and other cosmic phenomena. Through redshift, the light from distant galaxies becomes a narrative thread, weaving together the story of the universe's past, present, and future. Imagine cosmic strings as immensely thin, yet infinitely long and incredibly dense filaments of energy that could stretch across the universe. These theoretical structures, predicted by certain grand unified theories in particle physics and cosmology, are relics from the early moments after the Big Bang. Should they exist, a collision between cosmic strings would be a monumental event, capable of releasing enormous amounts of energy and potentially offering insights into the fundamental forces that shape our universe. One of the most striking consequences of a cosmic string collision would be the emission of gravitational waves. Unlike familiar gravitational waves produced by black hole or neutron star mergers, those generated by cosmic string collisions could be far more intense and offer unique signatures. These waves would ripple through space-time, carrying with them pristine information about the early universe and possibly revealing the underlying physics that govern cosmic strings. Detecting such waves could provide critical evidence for the existence of cosmic strings, thereby supporting theories that aim to unify the fundamental forces. The energy released in a cosmic string collision could also affect the distribution of matter in the universe. As these strings intersect and reconnect, they might generate high-energy particles, potentially influencing the formation of galaxies and large-scale structures. The interaction of cosmic strings with dark matter and dark energy could further alter cosmic dynamics in ways we are only beginning to explore theoretically. This cascade of effects could lead to observable phenomena, such as peculiar distributions of galaxies or anomalies in the cosmic microwave background, CMB. In addition to gravitational waves, the collisions might produce gamma-ray bursts or other high-energy astrophysical events. These bursts could serve as cosmic beacons, signaling the far-reaching consequences of such collisions. Astrophysicists would need to develop new observational strategies and instruments to detect and interpret these signals, opening up another frontier for understanding the extremes of the universe. Moreover, cosmic strings could give rise to exotic cosmological features like cosmic string loops, which could create gravitational lenses. These lenses might bend light in unprecedented ways, offering further opportunities to study the properties of cosmic strings and the fabric of spacetime. While the existence of cosmic strings remains speculative, their potential consequences, including the generation of gravitational waves, influence on large-scale cosmic structure, and high-energy emissions, make them an exciting subject of theoretical research. Future advancements in observational technology, particularly in gravitational wave astronomy, might one day provide the evidence needed to confirm or refute the existence of these fascinating cosmic relics. In the grand tapestry of the cosmos, supernovae play a pivotal role in the cycle of star formation and death. There are two primary types of supernovae, Type 1 and Type 2. Each has a unique mechanism and contributes distinctively to the cosmic dance. Type 1 supernovae, often resulting from the thermonuclear explosion of a white dwarf in a binary system, spew out vast amounts of heavy elements like carbon, oxygen, and iron into the surrounding interstellar medium. These materials become the raw ingredients for new star formation, enriching the molecular clouds that eventually collapse to birth new stars. Without these explosions dispersing heavy elements, the universe would have remained a less complex place, devoid of the rich variety of elements found in the periodic table. Type 2 supernovae, on the other hand, occur at the end of a massive star's life, typically more than 8 times the mass of our Sun. When such a star exhausts its nuclear fuel, it undergoes a catastrophic core collapse. The outer layers are violently ejected, scattering elements like silicon, sulfur, and even heavier metals like nickel and gold into space. This ejection process also triggers shockwaves that compress and stir up the surrounding gas clouds, often initiating the collapse of these clouds into new star-forming regions. These supernovae leave behind neutron stars or even black holes, contributing to the galactic landscape in a profound manner. Thus, through the spectacular death of stars, supernovae seed the universe with the essential elements and energy needed to ignite the birth of new stars, continuing the cyclical rhythm of cosmic evolution. The quest to identify what makes a planet habitable centers on several key factors that align with our understanding of life as it exists on Earth. One of the chief factors is the presence of liquid water, which is essential for all known life forms. To maintain liquid water, a planet typically needs to orbit within its star's habitable zone, commonly referred to as the Goldilocks zone, where temperatures are just right for water to exist in liquid form. Too close to the star, and the water would evaporate. Too far, and it would freeze. Thus, a planet's distance from its star, as well as its atmospheric composition and pressure, are critical in determining whether liquid water can be stable on its surface. Atmospheric conditions further dictate a planet's habitability by providing essential gases and regulating surface temperatures. A viable atmosphere provides a balance of greenhouse gases, maintaining a climate suitable for life through the greenhouse effect, which traps heat and moderates temperature extremes. A magnetic field also plays a crucial role by protecting the planet from harmful stellar radiation and cosmic rays, preserving both the atmosphere and potential biological organisms. Additionally, tectonic activity can be beneficial, recycling carbon and other essential elements through geological processes. Thus, factors like liquid water, a stable and protective atmosphere, a beneficial greenhouse effect, and geological activity collectively enhance the chances for a planet to support life as we understand it. The study of extremophiles, organisms that thrive in extreme environmental conditions on Earth, has revolutionized our understanding of the potential for life beyond our planet. These hardy organisms have been found in environments previously considered inhospitable to life, such as the acidic hot springs of Yellowstone National Park, the crushing depths of the Mariana Trench, and the dry, icy expanses of Antarctica. The ability of extremophiles to endure extreme temperatures, pressures, acidity, and radiation expands the range of environments where scientists believe life could exist. This widens the scope of astrobiological research, suggesting that life might not just survive but thrive in conditions far different from the moderate, temperate environments typical on Earth. For example, the discovery of thermophiles, which flourish at high temperatures, suggests that life could exist on planets or moons with volcanic activity, like Jupiter's moon Io. The presence of psychrophiles in the Antarctic ice hints that similar life forms might be found in the subsurface oceans of Jupiter's moon Europa or Saturn's moon Enceladus. Acidophiles surviving in highly acidic environments inform the search for life on Venus, where the atmosphere is predominantly sulfuric acid. By studying extremophiles, scientists develop a more comprehensive understanding of life's adaptability, thereby refining the search criteria for extraterrestrial life. Essentially, these resilient organisms underscore the tenacity of life, suggesting it might find a way to exist even in the seemingly uninhabitable realms of our solar system and beyond. The Drake equation is a probabilistic formula used to estimate the number of active, communicative extraterrestrial civilizations in our Milky Way galaxy. Conceived by the astronomer Frank Drake in 1961, the equation includes several factors that collectively help to quantify the likelihood of encountering intelligent extraterrestrial life. These factors are the rate of star formation in our galaxy, the fraction of those stars that have planetary systems, the number of planets that might support life per star with planets, the fraction of planets with life that develop intelligent beings, the fraction of civilizations that develop technology detectable from space, and the length of time such civilizations release detectable signals into space. Expressed mathematically, the equation is often written as N equals R star multiplied by Fp multiplied by Ne multiplied by Fl multiplied by Fi multiplied by Fc multiplied by L. Here, N represents the number of civilizations with which humans could communicate. R star signifies the rate of star formation in the galaxy, The parameter Fp is the fraction of those stars that have planets. The term Ni indicates the number of planets per star that are potentially habitable. Factor Fl is the fraction of those planets where life actually appears, while Phi is the fraction of life-bearing planets where intelligent life evolves. Fc denotes the fraction of civilizations that develop technology to communicate across interstellar distances, and L represents the average length of time such civilizations can and do communicate. While the parameters of the Drake equation are speculative, particularly the latter ones involving life's development and technological capability, the equation remains a valuable tool in the search for extraterrestrial intelligence, SETI. It frames the quest as not just a scientific endeavor, but a statistical one, guiding researchers toward understanding the factors that influence life's potential emergence and persistence in the cosmos. The equation has spurred decades of empirical research and theoretical studies, maintaining its status as a foundational concept in the field of astrobiology and the search for extraterrestrial intelligence. Missions like the Kepler Space Telescope have been instrumental in the search for exoplanets, planets that orbit stars outside our solar system. Launched by NASA in 2009, Kepler's primary mission was to survey a specific region of the Milky Way to discover Earth-sized planets located within or near their star's habitable zone, where conditions might be just right for liquid water and potentially life to exist. The telescope employed the transit method, which detects distant planets by observing the minute dimming of a star's light when a planet crosses in front of it. This tiny but measurable dip in brightness occurring at regular intervals is indicative of an exoplanet's presence and provides valuable data about its size and orbit. Kepler's contributions have been nothing short of groundbreaking. Over its mission, Kepler confirmed thousands of exoplanets and identified elements of their atmospheres, sizes, and compositions, thus dramatically expanding our knowledge of planetary systems. Its discoveries have ranged from Earth-sized rocky planets to gas giants larger than Jupiter, revealing an astonishing diversity of worlds. Some of these planets reside in their star's habitable zone, significantly boosting the number of places where life might exist. The wealth of data from Kepler continues to be analyzed, offering insights into the frequency of different types of planets, the architecture of planetary systems, and the potential habitability of these distant worlds. By profoundly enhancing our understanding of the universe's planetary inventory, Kepler has set the stage for future missions, such as the Transiting Exoplanet Survey Satellite, TESS, and the James Webb Space Telescope. These missions build on Kepler's legacy, aiming to further explore exoplanet atmospheres and search for biosignatures while continually narrowing down the list of worlds that might harbor life. Consequently, Kepler's enduring legacy is not just in its discoveries, but in the paradigm shift it has created in the search for extraterrestrial life. When searching for extraterrestrial life, scientists closely examine the atmospheres of exoplanets for specific signs, often termed biosignatures, that could indicate the presence of life. One of the most compelling potential signs is the presence of certain gases that, on Earth, are predominantly produced by biological processes. For instance, oxygen and methane are considered critical biosignatures. Oxygen, especially in large quantities, is highly reactive and would quickly bind with other elements, such as forming rust with iron if it were not being constantly replenished by living organisms, like plants and algae. Similarly, methane is produced by a variety of biological sources, including microbial life. The simultaneous presence of both gases is particularly intriguing because they tend to react with one another, so finding both in an atmosphere suggests a dynamic, ongoing source, potentially biological. Other potential signs include the presence of water vapor, which is essential for all known forms of life. Detecting water vapor in an exoplanet atmosphere suggests that liquid water might be present on the surface, creating an environment where life could potentially arise. Additionally, scientists look for complex organic molecules, such as those containing carbon and hydrogen, which are the building blocks of life as we know it. The detection of these molecules, particularly in patterns or concentrations that are not easily explained by non-biological processes, would be a significant indicator of potential life. Finally, scientists employ advanced techniques such as spectroscopy to analyze light from distant stars that passes through an exoplanet's atmosphere. This method allows them to identify the chemical composition of the atmosphere based on how the light is absorbed at different wavelengths. Future missions, such as those involving the James Webb Space Telescope, are expected to provide even more detailed observations, fine-tuning our ability to detect and interpret these subtle yet telling signs. By methodically searching for these biosignatures, scientists hope to uncover evidence that we are not alone in the universe. The icy moons Europa, orbiting Jupiter, and Enceladus, orbiting Saturn, present some of the most compelling environments for the search for extraterrestrial life within our solar system. Despite their frigid surfaces, both moons offer intriguing conditions beneath their ice that could potentially harbor life. Europa, known for its thick ice shell, has strong evidence pointing to the existence of a subsurface ocean kept liquid by tidal heating, a process where gravitational interactions with Jupiter and other moons generate internal heat, preventing the ocean from freezing solid. This vast, unseen ocean could be similar in volume to those on Earth, providing a vast potential habitat. Enceladus, on the other hand, has captivated scientists with its dramatic geysers that spew water vapor, ice particles, and organic molecules hundreds of kilometers into space from cracks near its south pole, known as tiger stripes. These plumes indicate not only the presence of liquid water beneath the icy crust, but also suggest hydrothermal activity on the ocean floor. Such activity is akin to the hydrothermal vents found in Earth's oceans, which are teeming with life despite the absence of sunlight. These vents create environments rich in chemical energy, capable of supporting diverse ecosystems through chemosynthesis, a process where organisms derive energy from chemical reactions rather than sunlight. Both moons' subsurface oceans and potential hydrothermal activities provide the key ingredients for life: liquid water, a stable energy source, and the necessary chemical compounds. Missions like the Galileo spacecraft, which studied Europa, and the Cassini spacecraft, which investigated Enceladus, have provided valuable data, but future missions aim to delve deeper. NASA's upcoming Europa Clipper mission, for instance, is set to conduct detailed reconnaissance of Europa's ice shell and subsurface ocean, while planned missions to Enceladus seek to analyze its plumes directly. These explorations could reveal whether either moon's hidden ocean conceals microbial life, pushing the boundaries of our understanding of life's potential in the cosmos. The discovery of phosphine in Venus's atmosphere in September 2020 sparked significant excitement and debate within the scientific community. Phosphine is a molecule comprised of one phosphorus atom and 3 hydrogen atoms. On Earth, it is associated with biological processes, particularly in anaerobic organisms, those that live in environments devoid of oxygen. The detection of phosphine was unexpected because Venus, known for its extreme surface conditions with temperatures around 800 degrees Fahrenheit and pressures 90 times that of Earth, is generally considered inhospitable to life as we know it. Phosphine is intriguing because its production in Venusian conditions presents a serious puzzle. On Earth, it is produced both by anaerobic microbial life and industrial processes, but Venus lacks the necessary industrial complex. This leaves natural processes as the primary suspects. Non-biological mechanisms such as photochemistry, lightning, or volcanic activity have been proposed, but these do not appear to explain the observed amounts of phosphine adequately. The possibility that microbial life might be lurking in the more temperate cloud layers of Venus, where conditions are mildly acidic and temperatures range between 30 degrees to 200 degrees Fahrenheit, suddenly seemed not so far-fetched. While the discovery of phosphine is far from definitive proof of life on Venus, it underscores the value of examining biomarker gases that could hint at biological activity, even in the most unlikely places. It also spurs renewed interest in Venus, prompting discussions of new missions to the planet to further investigate its atmosphere and surface. The revelation serves as a reminder that life might find a way to exist in environments radically different from those on Earth, challenging scientists to think creatively about where and how to search for extraterrestrial life. Future missions could provide much-needed clarification, potentially leading to one of the most profound discoveries of our time: the existence of life beyond Earth. Life on planets with extreme environments, such as high radiation or low temperatures, would likely require a range of unique adaptations to survive and thrive. On Earth, extremophiles already demonstrate how life can endure under such harsh conditions, providing a model for how extraterrestrial life might adapt, For instance, organisms exposed to high radiation levels, such as the bacterium Deinococcus radiodurans, have evolved efficient DNA repair mechanisms. These mechanisms allow them to rapidly patch up damage caused by radiation. Additionally, they possess protective proteins and antioxidant compounds that neutralize harmful reactive oxygen species generated by radiation exposure. If life were to exist on a planet with high radiation levels, similar adaptations could be expected, enabling organisms to repair their genetic material and shield vital biological processes from damage. In environments with extremely low temperatures, such as the icy moons Europa and Enceladus, life forms could adapt through several mechanisms. Psychrophiles, or cold-loving organisms on Earth, produce specialized antifreeze proteins that prevent ice crystal formation within their cells, which could otherwise cause lethal damage. These organisms also have enzymes that function efficiently at low temperatures, maintaining metabolic processes despite the cold. Additionally, the cellular membranes of psychrophiles contain high levels of unsaturated fatty acids, which keep the membranes flexible and functional in freezing conditions. Extraterrestrial life in similarly frigid settings might evolve to produce similar biochemical adaptations, ensuring cellular integrity and metabolic activity in cold environments. Furthermore, life in extreme environments might not rely on sunlight and photosynthesis as is common on Earth. Instead, it could utilize chemosynthesis, drawing energy from chemical reactions rather than light. This is observed in the ecosystems around Earth's deep-sea hydrothermal vents, where organisms convert energy from chemicals like hydrogen sulfide and methane to sustain themselves. On other planets and moons with no sunlight and high levels of other chemicals, chemosynthesis could be the cornerstone of such alien ecosystems. These potential adaptations illustrate the incredible resilience of life and its capacity to potentially exist in extreme, seemingly uninhabitable environments across the cosmos. The WOW signal, detected by astronomer Jerry R. Ehman on August 15, 1977, remains one of the most tantalizing mysteries in the search for extraterrestrial intelligence. Named after the exclamation "Wow" that Ehman wrote in the margin of the printout, this strong, narrow-band radio signal appeared to come from the direction of the constellation Sagittarius. What makes the WOW signal intriguing is its intensity and duration, lasting 72 seconds, and its frequency, centered around 1,420 MHz, a wavelength associated with the emission of hydrogen, the most abundant element in the universe. This frequency has long been considered an ideal hailing frequency by SETI, Search for Extraterrestrial Intelligence, scientists because it is a natural, cosmic quiet spot, less prone to interference by celestial noise. Despite numerous subsequent attempts to detect a similar signal from the same region, the WOW signal has never been observed again, leaving its origin unexplained. The implications of such a signal, if indeed artificial in nature, are profound. It would suggest that a technologically advanced civilization was intentionally transmitting at a frequency they presumed other intelligent beings would recognize. However, the inability to replicate the signal casts doubt and opens discussions on other possible sources, including natural cosmic phenomena or even terrestrial interference. Yet, the signal's singular nature, combined with its alignment with established theories about an ideal communication frequency, keeps it as a cornerstone case study in the search for extraterrestrial intelligence. Other unexplained radio signals from space add to the tapestry of cosmic mysteries. Fast radio bursts, FRBs for example, are incredibly brief, yet immensely powerful radio pulses that have puzzled astronomers since the first detection in 2007. While many FRBs have been linked to natural astrophysical processes, a few exhibit patterns that some speculate could be artificial in origin. Each new unexplained radio signal encourages more sophisticated observational techniques and theoretical modeling, pushing the boundaries of our understanding of both the universe and the search for other intelligent life forms. The WOW signal and similar unexplained phenomena remind us that the universe is full of unknowns, igniting curiosity and driving the continual advancement of both technology and theory in the quest to answer the age-old question, are we alone? SETI, Search for Extraterrestrial Intelligence. Projects employ a variety of sophisticated techniques and technologies to detect potential signs of alien civilizations, focusing primarily on the search for technosignatures, artificial signals or anomalies that would indicate the presence of advanced technology beyond Earth. One of the main methods used by SETI researchers is radio astronomy. The idea is to listen for deliberate signals sent by extraterrestrial civilizations across the vast distances of space. Radio waves are an excellent medium for long-distance communication because they can traverse the galaxy with relatively little interference. SETI projects typically scan a range of frequencies, concentrating on the water hole, a band between 1420 and 1650 MHz. This range is considered ideal for interstellar communication because it is bounded by the hydrogen line and hydroxyl radical emissions, both of which are fundamental components of water and thus might be of interest to other life forms. SETI instruments, such as the Allen Telescope Array in California, can monitor multiple star systems simultaneously, providing broad coverage. Advanced signal processing techniques are employed to sift through vast amounts of data to identify patterns or anomalies that stand out from the cosmic background noise. Researchers look for narrowband signals, which are much narrower than those produced by natural astrophysical processes, making them strong candidates for artificial origins. Additionally, they search for repeating signals, drifting frequencies that could indicate a transmitter on a rotating or orbiting platform, and signals that exhibit modulation, akin to how terrestrial communications encode information. Optical SETI is another innovative approach, scanning the skies for brief, powerful bursts of laser light. Unlike natural light sources, laser light is monochromatic and highly focused, allowing it to travel great distances without dispersion. If an extraterrestrial civilization aimed a laser pulse directly at Earth, it could stand out against the backdrop of natural stellar emissions, signaling an intentional attempt to communicate or announce their presence. SETI projects also utilize emerging technologies like machine learning and artificial intelligence to enhance their search capabilities. These tools can help detect subtle patterns and signals within the immense datasets collected, further increasing the likelihood of identifying potential techno-signatures. The search for extraterrestrial intelligence continually evolves with technological advancements, maintaining a hopeful yet methodical approach to answering one of humanity's most profound questions. Whether through radio waves, laser pulses, or other innovative means, SETI projects remain dedicated to exploring the cosmos for signs that we are not alone. Solar flares and coronal mass ejections, CMEs, are significant solar phenomena that profoundly impact planets and space weather. Solar flares are sudden, intense bursts of radiation emanating from the sun's surface, caused by the release of magnetic energy stored in the sun's atmosphere. These flares emit a broad spectrum of electromagnetic radiation, including X-rays and ultraviolet light, which can travel to Earth in about 8 minutes, affecting the planet almost instantaneously. Coronal mass ejections, on the other hand, are massive bursts of solar wind and magnetic fields that shoot vast amounts of charged particles into space. CMEs travel slower than solar flares, taking anywhere from a few hours to several days to reach Earth, depending on their speed and trajectory. When these solar events reach Earth, they interact with our planet's magnetosphere, the region dominated by Earth's magnetic field. Solar flares can cause radio blackouts by disrupting the ionosphere, a critical layer of Earth's atmosphere used for long-distance radio communications. The increased X-ray and ultraviolet radiation from solar flares ionize this part of the atmosphere, leading to a sudden spike in ionization levels. This spike can absorb or reflect high-frequency radio waves, degrading or completely blocking radio signals, which can disrupt navigation systems and aviation communications. CMEs have even more dramatic impacts as they can compress and distort Earth's magnetosphere, creating geomagnetic storms. When the charged particles from a CME collide with the magnetosphere, they can induce strong electric currents and generate intense auroras, commonly known as the northern and southern lights. While these auroras are visually spectacular, the associated geomagnetic storms can have serious consequences. These storms can induce geoelectric currents in power lines and pipelines, potentially leading to widespread electrical outages and damage to infrastructure. They can also pose significant risks to satellites, causing malfunctions or complete failures by damaging their electronic components. Astronauts in space are also vulnerable, as increased radiation levels can pose serious health risks, necessitating protective measures during heightened solar activity. Beyond Earth, solar flares and CMEs affect other planets and space weather throughout the solar system. For example, Mars, which lacks a global magnetic field, is more exposed to these solar events, which can strip away its atmosphere and expose the surface to high levels of radiation. Understanding and predicting solar activity are crucial for mitigating these impacts, protecting technology, and ensuring the safety of space missions. Through continuous monitoring by satellites like NASA's Solar Dynamics Observatory, SDO, and the European Space Agency's Solar and Heliospheric Observatory, SOHO, scientists strive to forecast space weather events and enhance our preparedness for the sun's dynamic behavior. Auroras, often referred to as the northern and southern lights, Aurora Borealis and Aurora Australis respectively, are mesmerizing natural light displays predominantly visible near the polar regions of Earth. These radiant phenomena are the result of complex interactions between solar wind and a planet's magnetic field, specifically its magnetosphere. The process begins with the solar wind, a continuous stream of charged particles, mainly electrons and protons, emanating from the sun. When these particles encounter Earth's magnetic field, which extends far into space, they are guided by its lines of force toward the polar regions where the field lines converge. As the charged particles spiral along these magnetic field lines, they are funneled towards the Earth's upper atmosphere, particularly into the regions known as the auroral ovals, which encircle the magnetic poles. Once the particles enter the upper atmosphere, they collide with molecules and atoms of gases, such as oxygen and nitrogen. These collisions transfer energy from the charged particles to the atmospheric gases, exciting the gas atoms and molecules. In simpler terms, it knocks electrons within these atoms and molecules to higher energy states. After an atom or molecule has been excited, it eventually returns to its original lower energy state, releasing the previously absorbed energy in the form of light. The specific color of the aurora depends on the type of gas involved and the altitude at which the collisions occur. Oxygen, for example, produces green or red light, which is the most common auroral color. Green light typically occurs at altitudes of around 60 to 150 miles, while red auroras usually happen at higher altitudes around 200 miles. Nitrogen, on the other hand, contributes to blue or purplish-red hues. The combination of these colors can create dazzling, multicolored displays that ripple and dance across the sky. Auroras are not unique to Earth and can occur on other planets with strong magnetic fields and atmospheres. For instance, Jupiter and Saturn, both of which have significant magnetic fields, also exhibit spectacular auroras. Jupiter's auroras are especially intense due to its powerful magnetosphere and the presence of its volcanic moon Io, which supplies a substantial amount of charged particles. The study of auroras provides valuable insights into the intricate workings of planetary magnetospheres and atmospheres, as well as the broader dynamics of space weather. By understanding these processes, scientists can better predict geomagnetic storms and their potential impacts on technology and human activities. Auroras thus serve as both a natural wonder and a crucial window into the interaction between our planet and the broader cosmos. Tidal forces exerted by black holes have profound and often dramatic effects on nearby objects and stars, owing to the intense gravitational fields associated with these cosmic entities. These forces arise because gravity is stronger at the point closer to the black hole and weaker at the point farther away. This differential in gravitational pull can stretch and distort objects in a process known as tidal stretching or tidal interaction. The closer an object gets to the black hole, the more pronounced these forces become. For stars that venture too close to a black hole, the tidal forces can be catastrophic. As a star approaches the event horizon, the boundary beyond which nothing, not even light, can escape the black hole's pull, it experiences increasingly extreme tidal forces. These forces can stretch the star into an elongated shape, and if the star crosses a critical distance known as the tidal disruption radius, can tear the star apart in a dramatic event known as a tidal disruption event, TDE. During a TDE, the stellar matter gets drawn into long streams. Some of this material may form an accretion disk around the black hole, radiating immense amounts of energy and producing intense flares and bursts of X-rays and gamma rays observable from Earth. The rest of the stellar debris can be ejected into space at high velocities. Even objects that are not consumed entirely by the black hole can experience significant gravitational effects. For instance, orbiting stars and gas clouds can be accelerated to very high speeds, resulting in energetic emissions that help astronomers study the environment around black holes. In more densely packed regions, such as within globular clusters or galaxy centers, black holes can significantly influence stellar orbits, leading to complex and dynamic interactions. These effects are especially pronounced in supermassive black holes situated at the centers of galaxies, where they can dictate the motion of thousands of stars over vast distances. The study of tidal forces around black holes not only enhances our understanding of these enigmatic objects, but also provides valuable insights into the behavior of matter under extreme gravitational conditions. The disruptions caused by black holes can also play a significant role in galactic evolution, influencing star formation rates and triggering energetic processes that can shape the interstellar medium. Understanding these interactions is crucial for painting a complete picture of the life cycles of stars and the dynamics of galaxies across the universe. Cosmic voids are vast, expansive regions in the universe that contain relatively few galaxies, stars, or other forms of visible matter. These empty spaces are immense, sometimes spanning hundreds of millions of light-years across, and are surrounded by denser regions of the universe, such as galaxy clusters and superclusters. Despite their apparent emptiness, cosmic voids are incredibly informative about the large-scale structure and distribution of matter in the universe. The existence and characteristics of cosmic voids provide critical insights into the principles of cosmology, particularly the distribution and behavior of dark matter and dark energy. From a theoretical standpoint, the universe's structure resembles a cosmic web composed of filaments of galaxies and dark matter separated by these vast voids. According to the standard model of cosmology, cosmic voids arise from the gravitational effects of dark matter. Shortly after the Big Bang, slight density fluctuations in the early universe led to regions of space with varying gravitational pull. Over billions of years, gravity pulled matter into denser regions, forming galaxies, clusters, and superclusters, while less dense regions expanded to become the voids we observe today. By studying cosmic voids, scientists can gather valuable data on how the universe expands and evolves. The properties of voids, such as their size, shape, and distribution, offer clues about the rate of expansion of the universe, helping to test and refine models of cosmological expansion driven by dark energy. The greater the number and size of voids, the more insights we gain into how dark energy influences the separation of galaxies and the overall geometry of the universe. Moreover, cosmic voids can help improve our understanding of the nature of dark matter. Since dark matter interacts primarily through gravity, its distribution affects the formation and evolution of cosmic voids. By mapping the patterns of galaxies and voids, researchers can infer the underlying dark matter distribution, providing insights into one of the most elusive components of the universe. Additionally, because cosmic voids have relatively low gravitational influences and lower temperatures compared to denser regions, they offer a relatively clean environment for cosmic microwave background (CMB) studies. Space within voids can allow for more precise measurements of the CMB, the afterglow of the Big Bang, without significant interference from hot, dense galaxy clusters. Cosmic voids are not just empty spaces. They are key components of the cosmic landscape that deepen our understanding of the universe's structure, the behavior of dark matter and dark energy, and the overall dynamics of cosmic evolution. Their study continues to be a crucial element in modern cosmology, aiding in the ongoing quest to unravel the mysteries of the universe. Imagine looking through a giant cosmic magnifying glass, one that's not made of glass but of pure gravity. This is how scientists use gravitational lensing to study distant cosmic objects. When a massive object, like a galaxy cluster, lies between an observer and a faraway galaxy or quasar, its intense gravitational field warps space-time. Albert Einstein's theory of general relativity explains this phenomenon. light from the distant object bends around the massive intermediary, much like light bends in a regular lens. This effect can magnify and distort the background object's image, allowing astronomers to observe details that would otherwise be too faint or too small. Gravitational lensing isn't just about making something faint appear brighter. It's a cosmic detective tool. By analyzing the patterns of light distortion, scientists can infer a wealth of information about the foreground and background objects. They determine characteristics like mass distribution in the intervening galaxy cluster, uncover the presence of dark matter, and even detect exoplanets. To put it in perspective, some background objects lensed by massive galaxy clusters are so distant that we see them as they were more than 10 billion years ago, offering a rare glimpse into the early universe. This cosmic magnification helps astronomers map the large-scale structure of the cosmos, unveiling secrets that lie hidden in the fabric of space-time itself. Do you think there could be other forms of life in the universe? Let us know your thoughts and ideas in the comments below. Thanks for watching.